What's up, numbnuts? It's 8 o'clock on a Friday holiday morning, but it's time to do some calculus. This is the ultimate Calc 4 review. Now, this should cover everything from 15 points. This will cover everything from 15.7 to 16.3. If you're not familiar with the sections, that's cylindrical coordinates, integration using cylindrical coordinates, all the way to the fundamental theorem of line integrals. Okay. And these are all the formulas you're going to need. I have them all right here. And before you start trying to write down everything, look in the description. I will have all these slides posted. I'll have the template. So if you don't want to just listen to the video and you want to do the problems on your own, you could download the template. And then later on, if you want to check things, when you check everything, you could also download the completed notes, which is what I'm going to have here. Right? I'll complete everything. So it's like a worksheet and a solution manual, right? And if you're confused at any moment, you can always go back. There'll be timestamps, right? So I will try my best to make this as user-friendly as possible, so you're not stressed out. Okay, well, besides that, let's get into it. Problem 1. Well, first off, let's read the problem. We can't just start trying to put things in. Okay, we have a cylinder, the radius 1. We have another cylinder with the radius 4, right? Remember, we have to take the square root of that. And it's above the xy plane and below the z equals y plus 4 plane. Okay, well, let's think in our head what this would look like before we even draw it. Okay, so it's gonna, if we're just doing a projection onto the x and y plane, look like a donut, right? Would have a, we'll have like an inner radius and then a outer radius, right? And then if we were to think about this in terms of like what the other stuff is saying, what does the xy plane mean? It says it's above the xy plane. Well, it's above where z is equal to 0, right? So it never goes into the negative z space. And then it's below where z is equal to y plus 4. So it's this donut, and then it's like cut at the top, cut at the bottom, and at the top it should be cut kind of like that, right? Okay, so we already have a picture in our head, and I'm actually not going to bother to draw this because I think that would just be wasting time. If you want to, you could, but you really don't need to find the bounds in this case because they're actually going to be fairly nicely straightforward, in my opinion. I could just be lying out my ass. It could be really complicated. Yeah, well, let's just start with the given, right? So remember cylindrical, we have to find the z-bound. Okay, so we know 1 is definitely 0, right? That's the xy plane, right? It's above the xy plane, so if it's above it, that means it has to be the lowest one, right? And below the y plus 4. Okay, so look at that. We already found one bound. Okay, we gotta do a little bit more now. 2 cylinders. Okay, well, like I said earlier, I'll draw this domain though. We're just focused on this area, right? And if you had to describe that using polar, right, you would say that it is, what is it? Okay, r theta, where r is from 0. Not 0, right? What's our minimum radius? We gotta think about the smallest cylinder. Minimum radius is 1. Nope. Minimum radius is 1. The largest radius is 4. Okay, and then is the angle of the cylinder bounded? No, it's not. It's from 0 to 2 pi. It's a complete cylinder. Hey, we already got that part done. Look at that. I mean, you get like almost majority of your credit right just from knowing those few things. Do the integral. I always like putting the pi on the back. Why? Because I don't want pi's floating around later. And we got 4, 1, and y plus 4. Nope. Should be 0 right here. And x minus y. Well, what does x minus y actually mean? Well, x minus y, for using polar, would be r cosine theta minus r sine theta, right? So r cosine theta minus r sine theta. And then don't we have A Jacobian here? Yeah, we do have a Jacobian. It's R. R. And then we got dr. No, we don't have, we do have dr. But then it goes dz, dr, d theta. Ignore the very ugly r's here in this case. I ain't saying no hard r's, that's why I don't draw good r's. Okay, so this is our integral setup, right? And like I hate when people draw the integral symbol like 3 times when they're doing this. It's like you don't need to do that. You only need to draw it once because you can only do one integral at a time. And I'll explain what I mean in a second. You'll see what I mean. Okay, so first integral we're gonna do is strictly everything but just r's, right? I mean strictly everything in the z. Look at that. There's no z. It's just, well, I mean there's one. One is our z. So this just turns into y plus 4 minus 0. You don't really have to draw the minus 0. I don't know why I did that. And then, what is that? That's r sine theta plus 4. But then, now we have to move that into our next integrand. So our next integrand is going to be from 4 to 1. Make that look like more of a 4. Right, it's going to be from 4 to 1. And we're just thinking about r's here, but so we had an r here, we had an r here, r here, and we're going to multiply it by this. So we'll have r sine theta plus 4 times r squared, 1 second, r squared cosine theta minus r squared sine theta. And like I said, right, you do the first integral and it's going to carry on into the next integrand. That's how triple integration works, right? So you did your dz integral, produce this, then that integrand times this integrand. Notice I times the r in here, that's why there's r squared here. Okay, well, we just have to kind of FOIL this out real quick. And okay, so r sine theta times r squared cosine theta, I see that as, let's write r sine theta times r squared, so God, I can't say it. It's r cubed sine theta cosine theta, and then let's do r sine theta times r squared sine theta. Let's not forget that negative. r cubed sine squared theta, yeah. Okay, so we got r cubed sine squared theta, and then what else? Now we gotta do it with the 4s. Oh my God, you're like, this integral's getting really big really fast. Yeah, it is. I mean, that's the tip actually, right? It's like, just be a little bit uncomfortable, right? Just be a little bit uncomfortable for a little bit. And then we'll see that this giant integrand will probably actually simplify down to something pretty nice. If not, I mean, that's just a dick move on the book's part. All of this integral is directed to dr, and you can't even see that anymore. Put my face over here. That's what we get, right? That's our integrand. It's huge. Maybe we can rewrite things a little bit, right? Maybe we can. Let me think here. We have sine. Well, let's just check if we did correct. Sine, cosine, sine. Okay, yeah. This looks fairly correct to me. I don't see mistakes. If I do, well, we'll find out. Okay. And like we said, we're only focusing on the dr, so actually I'm not going to rewrite anything. I'm actually just going to keep it like this. But I will do, no, I am going to rewrite it because this is ridiculously long. I could do one little trick to make it a little bit smaller. Okay, 4 to 1. It's from 4 to 1. I'm going to write up the r cubed here, sine theta, cosine theta, sine squared theta, plus 4r squared cosine theta minus sine theta. Again, remember all this is with respect to dr, so really you only got to focus on r's when you're integrating. What would this become? Well, this would become r4 to 4 sine theta cosine theta minus sine squared theta plus 4r cubed divided by 3 cosine theta minus sine theta. And all of this is going to be evaluated from 4 to 1. And yeah, well, here, this is like kind of a pain to actually put in these bounds. So we're going to do a little bit of a trick here. Totally valid trick, as long as we just don't mess it up. We integrated with respect to dr, so we don't have to touch the r's again. That's the only thing we're going to touch here. So I'm going to write this as, okay, so r to the power 4 will become 4, okay, I'll just write here, 4 minus 1 to the power 4. Okay, and I'm just going to write trig. Why? Because, like, I don't have that much space. We're going to rewrite it later, don't worry. We get 4 over 3, 4 over 3, and it's going to be 4/3 minus 1. Why can I do this? Well, I mean, guys, like I said, we're only touching r in trig 2. Okay. And let's actually think about this. Okay. Well, 4 to the power 4. Ooh, I think that's 16 times 16, which I know to be 256. How I know that? I know 15 times 15 is 225 because that was like my highest bench. Okay. So it's a little bit. So 256 minus 1, 255 divided by 3. Okay. So the next integral will be 2 pi to 0, 255 divided by 3. And then what's the trig thing? The trig was, what's the trig thing? Come on, man. Sine theta, cosine theta minus sine squared theta. I'm going to split this into 2 integrals right now, because why would I want to make my life miserable and have so many integrals around here? Okay, and 4 to the power 3, that's 64. 64 minus 1 is 63. 63 times 4, that's some hard math. That's 60 times 4, which is 240. 240 times 240 plus 12, 252. 252 divided by 3. And let's think. 252 divided by 3. What can we say that? That's nearly 80 times 3, right? If it's nearly 80 times 3, let's just think of, okay, no, 82 would not be enough. Let's think it's 83. 83 times 3. No, that's not it. How about 84? 84 times 3? Okay, 80 times 3 is 240. 4 times 3 is 12. Yeah, okay, look at that. It's 84. Next, so it's 84. 84 2 pi to 0. And what's our next? All that trig crap here is 2 cosine theta minus sine theta d theta. Okay. So yeah, that's the last integration parts we have to do. And since, you know, like, it's just really not enough space here, I'm going to call this part 1 and part 2. I'm going to make some space real quick. Let me just drag this thing down. Oh god, this is going to be kind of hard to do here. Now, as I'm doing this, I want people to think about some trig identities here of how to make these integrations a little bit simpler. I personally see, I know that sine cosine theta times 2 is a trig identity. I just know that. I forgot the last part. I'll have to look that formula up. I know it's the sine squared formula. And then cosine sine theta, we actually don't need that. So how about we just, oh, I got to pause the recording. I only have 15-minute clips and I got to restart real quick. Okay, so we're back. Yeah, I have like a free screen recording program, so I have to take 15-minute clips. So as you can see, this is going to get kind of bothering on my part, but you won't notice it. Hey, part two, I want to do part two integral first because it's simply easier. Okay, part two, 84, 2 pi, why am I rewriting it? It's there. You guys know what it looks like. Okay, 84, hold up, we'll call it I2, just so people don't get angry. Yeah, that's the same thing. That's part two. I2 is part two, just integrated. Okay. Cosine theta, what does that turn into? That turns into sine theta. Negative sine theta turns into positive cosine theta. Right? So if we're to take the integral of, if we're to take the derivative of cosine theta, what we would get negative sine theta. Yes, the theory holds. And let's think. Okay, so sine theta at 2 pi and 0 is always going to be 0. So we only actually have to think about cosine. I'm just going to kind of scratch that right there. Okay, so cosine of 2 pi is 1. Cosine of 0 is 1. Thinking real hard for a second. Okay, so like I said, 84, the sine will be 0 at any point. The cosine will be 1 at both points. If we know that, then we're essentially think about it like we're integrating just a cosine curve, right? So just this, and if it's at cosine of 2 pi is 1, cosine is 0, so 1 minus 1 is 0, right? So part I2 is, let's write 0 here, just equal to 0. I2 0. Okay, let's do the second part. Let's do I1, which is P2, 2 pi to 0, d theta. Okay. Oh, no, 255. Yeah, why are we scared? It's just a constant. No reason to be afraid of a constant. Okay. Sine theta, cosine theta. Okay, what's it called? I'm going to pull up my trig sheet to show you guys. Where is it? I need to find it. Window. Okay, here it is. Let's go to trig. This one, I don't have the 2 sine theta one. Okay, look at it. 2 sine theta cosine theta is equal to sine 2 theta. Okay. So we're going to rewrite the integral as, first we need to think about it. We can't just do it directly. I'm going to put a little bit of this work in green all the way over here in this little box. Okay. So 2 sine theta cosine theta is equal to sine 2 theta. But we don't have a 2 in front of there. So we'll just write it as sine theta cosine theta sine 2 theta divided by 2. And then, okay, I just know this other one by heart, truthfully. It's 1 minus, it's always minus for sine here in this case. Cosine 2 theta divided by 2 is equal to sine squared theta. Okay, yeah, I know that's kind of messy, but I mean, running low on space here because I'm new to this whole thing. Okay. So this is going to turn into what? Sine, right? Sine 2 theta divided by 2 minus 1/2 So I'm going to distribute the minus in, so it's minus 1/2, then, right? So minus 1/2, then plus 1/2 cosine 2 theta. And if you're really getting irritated about the fact that there's 2, 2, and 2 here, yeah, you could make it 255 divided by 6. But I like to be uncomfortable. So this is, okay, I'm going to do it now. Not uncomfortable anymore. So it's 255 divided by 6. And then sine, the antiderivative of sine 2 theta will be negative cosine 2 theta divided by 2. The antiderivative of 1, because this is 1 because I put the 2 on the outside, is minus theta. The antiderivative of cosine 2 theta would be sine 2 theta divided by 2. All this is from 2 pi to 0. Now we just need to evaluate all this junk. Okay, well, 255 6. Okay, cosine. Let's just think here. Cosine. Oh, well, cosine will be 1 in both of these cases. The sine will be always 0. So, like I said, it's not like this doesn't exist. It's just for the evaluation, this will be 0. Okay, it's not that it doesn't exist. Just evaluate at both points, it will be 0. Okay, so we only need to think about this integral really, right? I mean, this, not integral, this product right here. Okay, so cosine 2 theta would, if you plug in the 2 pi, that would be negative cosine 4 pi, which is the exact same thing as negative cosine 2 pi, which is 1. Negative 1/2 minus 2 pi. I'm going to give you a minus, right? And let's think here, well, that would just be 1/2. Okay, so if cosine is 0, cosine 0 is 1. Negative 1/2 plus 0. All right, just write the 0 there, just for extra credit. Okay, now we got to do this math here. This would be positive 1/2. This would be positive 1/2. A positive 1/2 and a positive 1/2. They make them go away. And we just are left with the negative 2 pi, which this would turn into 255. If the 2's here and there's a 6 here, that's the same thing as 255 negative. Okay, so minor mistake, right? And I like to do these completely live, not looking at anything, because I like to show that, you know, this is where mistakes come from. Now, problem with doing math in your head, I don't actually recommend it, is you forget about little things. Remember, this was a 4. When did it turn into a 3? How did a 4 turn into a 3? Right? It turned into a 3 over here. So should be 4, right? Let me write it as 4. This makes me really sad that I messed up on things like that. By the way, I believe if you mess up on something like that, you probably wouldn't be marked off any points. So I'm just gonna edit it, right? So wherever you see the 3 under 255, it should be a 4. And then, right, this 3 over here would turn into a 4. And then the 6 would turn into 8, right? Turn into 8. This would turn into 8. And then what would this be? This would be 255. Like I said, the 1/2s go away. If there's a 2, 2/8, 255 pi divided by 4. That's the correct answer. And I know it because I do have the solution manual, right? So that's confirmed. Now, earlier, let's just recap. We saw that this turned out to be 0, which is pretty nice. And we just had to do, we saw that we could ignore the sine 2 theta over here. And then the rest was just a lot of multiplication with negative signs. Important things to look back on, before we did all that, is we had to define that we had two radiuses, right? We had a minimum and we had a maximum radius. In this case, the minimum radius is not 0, right? Because it's not starting at the origin here, right? It's actually starting at the smaller cylinder and extending to the larger cylinder. Okay. And then later on, another useful thing that we had to do here is we saw that we had to use the trig identities, and these trig identities are in green right here. Okay. So that's all for this problem. Let's do the next. Let's see how far we can get in the next. I only have 4 minutes to try to do this, and then I have to restart the recording. Okay. So we have a sphere, we have a cone. What does that say? Well, I actually know from 15.8 that this problem probably pops up again in 15.8, but we want to do it using cylindrical, and it probably won't be that bad using cylindrical. It might even be easier than if we were to try to do spherical coordinates, because then we'd have to find our angle phi, and then we would also have to indicate that we are just using a complete different change than something that we're familiar, like polar. Alright, so let's just do this using cylindrical. Okay, we have z is equal to that. Now, notice that this z is positive, right? So it's really, and that this z, let's read this problem again. Find the volume of the solid enclosed by a cone. Alright, so I know this seems like there's not enough space, but I actually paused the recording and I added extra page. So we will have enough space for this little part. We're just going to find the bounds and we'll do the integration on the next page. Right. So if we read this, we have a cone and we have a sphere, and they both are actually centered at the origin, right? They both start at the origin. It's not shifted here. We don't see any shifts. And we want to know the volume of the solid enclosed by both of those shapes. Now, what makes this problem hard, in my opinion, is what's bigger, the sphere or the cylinder? Now, some of you guys may just guess the sphere, which the answer actually is yes, it is the sphere. But sometimes you're not able to know, and sometimes you're like me, you don't want to guess, or you can't see it, you just can't picture it in your head, right? Because it's 3D shapes. I don't have a bunch of cones and spheres laying around my house. I mean, right? Okay, so let's just think about how we can first find a few of these bounds. Well, let's start with the easiest. Cone and sphere, if you project them both onto the xy plane, x plane, right? Why is this not showing up? Well, there's a delay in my screen right now. Okay, yeah, it popped up now. Good. So we have a y, an x plane, and this is the shadow of both of those shapes. They both fill it up. And they both go from 0, theta, 2 pi. Although, you don't know the radius. For all we know, let me erase this drawing here, redraw it. For all you know, it could be something like this, right? Where this is the sphere's radius and then the cone is bigger. Or, I'm saying, you don't know the radius is truly, but you do know that it's going to be from 0 to 2 pi, right? There's no abrupt stops. It's not half of a cone, half of a sphere. You know that for a fact. So that's your given radius, right? You can at least get that down. But what about r? What's a radius? That begs the question. What's a radius? Well, I bet you could find the radius by using z. Okay, so we have z over here. Let me use this. We have z equals x squared plus y squared. And we got the sphere equation. Well, what if I turn this into z squared? And then what if I solve for z squared here? Let's do it. So we would see that z squared is equal to x squared plus y squared, which is equal to, remember, I just want z squared by itself here, so it's going to be 2 6 squared minus y squared. And if we insert our polar equation of x squared plus y squared is equal to r squared, we know this is r squared minus 2r squared. Okay, so that all makes perfect sense, right? I mean, all we did is set z squared equal to z squared, and then we just inserted r squared, right? Well, that doesn't give us exactly what we want, but it gets us a lot closer. Okay, so we can take those two facts, and then I'm going to add the minus r squared to the left-hand side. So we get 2r squared is equal to 2. And obviously both of the 2's can cancel each other. So r is equal to plus or minus 1. Yeah, the plus or minus, right? Because don't forget plus or minus when you take square roots. You'll see in a second that that will become useful. But not for this problem. For radiuses, just in this case, because we know it's centered at the origin, we have a radius of 0 and 1. Yeah, we have a radius of 0 because it's centered at the origin, right? So that's kind of a secret here. I mean, there's no algebra that actually really shows that in this case. At least I didn't show it. And then we assume that we have a positive radius because we don't have a negative radius for this case, right? And it's polar here, so this is as nice as it's going to get for us for finding our r. So I'll write our r bound here. 0 to r to 1. Okay. So that's the common radius, right? That's the common radius that both of those shapes have in common. So if I was to draw the picture now, right, 1. So even though maybe the sphere is bigger, maybe the sphere is bigger, we're only integrating the volume that both of them share, right? So they need to have a common radius, and that common radius is 0 to 1. Anything from 0 to 1, that's what both of them share. Okay. Now here's the harder part, is we want to find our z bound, right? Cylindrical, we integrate from theta to r to z. So we need z. Okay, well, z is equal to x squared plus y squared, which is the same thing as r squared, which is the same thing as r. And then z is equal to, this is z squared, right? So what am I going to do? I'm going to take the square root of that. Plus or minus. Now, x squared minus y squared is the same thing as minus r squared. Okay, and now I'm going to do this purely because I've done a bunch of these problems, and I know how they work out, and I know the intuition here, okay? I'm going to drop the negative sign here. So it's just going to be r is equal to 2 minus r squared, which is equal to z. Okay, but we don't know which one's bigger. We don't know which equation for z is bigger. But we do know r is from 0 to 1. So this is my favorite part, right? It's where most people lose points. If you don't lose points on this, you'll be really happy. Okay, so which one's bigger again? That's the question. Well, I would argue that r is equal to 2 minus r squared at 1, because that's the common radius, right? They both share that. They have to be equal, right? Plug it in. 1, right? That becomes 1, and this is equal to 2 minus 1 squared, which is 2 minus 1. 1 squared is 1, so z is equal to 1. Okay, so they're both equal at 1. How about 0? Okay, well that's 0. And then this is equal to 2 minus 0. Well, okay, square root of 2 is definitely bigger than 0, right? And if you wanted to go one step farther to prove it to yourself that this is bigger than this, put in any point between these. So you could put in 1/2. So 2 minus 1/2 squared is 2 minus 1/4. 2 minus 1/4. Pause for a second. You do the math yourself. That's definitely bigger than 1/2, right? There you go, right? So now we know which is bigger, and we have our z bounds. So let's write it. We have z. We have r to z to 2 minus r squared, yeah, square rooted. Okay, so that is like 90% of the problem done, okay? Now I'm going to flip the page. We're going to actually integrate this now. Okay, so let's do the integration. And we're going to try to go kind of fast here. Actually, we're not going to try fast. 1 to 0. 2 minus r squared. R. Okay, it's dz r dr d theta, right? Don't forget your r dr d theta. Okay, well, like I like to say, is the first integral is root 2 minus r squared over r dz. You can see that this just turns into 2 minus r squared minus r. And then remember, we have to multiply this by r for our next integrand. So times it by r, and then this turns into the integral from 1 to 0 of r 2 minus r squared minus r squared. Right? There we go. Okay. Now, what's super nice is that Jacobian, because I would not want to integrate just the square root 2 minus r squared. That'd be much more of a hassle. Put my face over here. But we have that r, we times it by r, so now we can actually integrate this a lot easier. Now, me personally, you don't need to do this, you really don't. But I'm going to break it into 2 integrals just because it just helps me mentally. Okay? Like I said, you don't, there's no reason why you need to do that. No. Don't forget your differentials, you'll get marked off points. Okay. Okay, so let's go with this one. Let's go with this one. We'll call this I1 and I2. Okay. Well, I1, let's do I1 first. Okay, well, okay. I think everyone here can see that you're going to have to do some sort of substitution, or else it's going to be kind of a harder thing, not a harder integral, right? If you don't do the substitution. Now, if you're thinking about it, what do you want to get rid of? You want to get rid of that r in front, right? You want to get rid of that r in front. That's kind of making our life a little bit hard. At the same time, it's going to kind of make your life easier, you know, because you do need that r in front to actually make a legitimate substitution here. So if we let's just pick a variable here. I like to say a. If we let a be 2 minus r squared, then dA, the derivative of a, is going to be, one second, minus 2r dA. Okay. And then if we're converting from r into a, let's make a table. Shows that, helps us with it. So we have our bounds for r is 1 and 0. So let's think about this. If we put 1 into a, so a of 1 would be 2 minus 1, which is 1. And if we put 0 into a, so a of 0 would be 2 minus 0, which is 2. Okay. So we have this going from 1 to 2 of r a dA, okay, divided by negative 2r, right? Remember, oh, one second, minor mistake here. This should be a dr. I don't know why I wrote dA. No, it should be dA. This should be a dr. My bad. My eyes just always mess up on me. Okay, so right, if you want to get that dr by itself, divide by negative 2r and replace that, right? This is our substitution. And as you can see, the r's will go away. All right, so I'm gonna show the r's go away. And then focus on this part, right? We have a negative 2 here. And we have a 2 and a 1 here. So our bounds are going from big to small, which means negative, right? But we have a negative here, so I could rewrite this whole integral as the same thing. It's the exact same thing as this. It's the exact same thing. All you did is just flip the bounds, and that gets rid of the negative, because a negative times a negative is positive. Okay. So if we do this integral, we get 1/2. 1 second. A is 3/2 divided by 3/2 from 2 to 1. And as you can see, we can see that we can't see yet. Maybe I'll rewrite it a little bit nicer, then we can see, right? Okay, now we can see that the 2's go away, and it's just a 3/2, 2 to 1. Where this is going to have to equal 1/3 to 2 to the power 3 over 2 minus 1. 1 to the power of anything is 1, right? Even 1 to the power 0 is 1. Okay, here we go. Now let's just maybe simplify I1 a little bit more, because it may just help for later. We could write that as 2 square rooted minus 1 over 3. That's I1, okay? Now I2, we want to do I2 here. Let's do I2 over here. Okay, I2, what? Oh, well, that's the same thing as -1 squared dr1 to 0, which is going to become -1/3 r cubed 1 to 0, which is -1/3. Okay, that's all it is. So now we got to add I1 and I2 together. I1 plus I2. They look at that. They both got the same denominator, so this is just going to become 1/3 square root 2 minus 1. Wait 1 second. I did. Yeah, minus 1. Okay, last you guys saw is I1 plus I2, and then the recording cut, because I have a really shitty program and only takes 15-minute clips. This is what you get, okay? If you add I1 and I2, I1 is here, right? I2 is here. You can see that they both have the same denominator, and then you can factor out the 2 later, okay? Well, we could write this as I1 plus I2, and we got one more integral to do. But it's my favorite one because it's just 2 pi to 0 d theta, which means it's just 2 pi sum of the I. Right, this is just being fancy, just taking little shortcuts here. Which is the same thing as 4 pi over 3 square root 2 minus 1. And that's our final answer. That's the volume within inside those two spheres. That's their combined, not combined volume. That's their merged volume. So where they merge together, that's their volume. Okay. Okay, now we're on to 15 point, spherical coordinates. Let's read the problem. We have a cone with the angle phi equals pi over 3. And below the sphere, p equals 1. Look at that. They give us just 2 pieces of information, really. And they're going to find triple integral using those 2 pieces of information. Okay, now, the most important part, besides those actual numerical values, like pi over 3 and 1, is, look at this, above the cone and below the sphere. Okay, so with that information, let's make some conclusions. Okay, now I'm going to argue that this is the maximum angle phi, okay? They're just kind of giving it to us, which is really nice. And I'm going to argue that this is the maximum radius, not, okay, well, rho, let's call it a radius here, right? It's the maximum radius here. And they're also just giving that to us. And let's just think, like, we have a cone and we have a sphere. If we were to think about the shadow that both of those create, it's a circle, right? Like, if you were to stand on top of a cone, it would be a 2D plane. That 2D plane would be a circle. Same thing for a sphere, okay? So we got 0 to theta, 2 pi. Oh, look at that's very nice. I mean, that's all it is right there. That's the bounds. Now let's integrate. Okay, so we're gonna have 2 pi, 0, pi, not pi to 0, pi over 3 to 0, and 1 to 0. Okay, y squared, z squared, we'll just write it. And then don't forget your Jacobian here. Your Jacobian is p rho squared. Stop saying p. Rho squared sine phi. And you got dp, d phi, d theta. Okay, now if you don't remember what y squared and z squared is using spherical coordinates, I'll write out what y is equal to. Well, y is equal to p sine phi sine theta. And I believe z is equal to p cosine phi. Now, obviously, if there's no cuts, that means it's correct. Okay, so let's rewrite those. Let's actually just make a little box here where we do y squared, z squared, rho squared, sine phi is the same thing as rho squared, sine phi squared, sine squared theta, rho squared, cosine squared phi, sine phi, rho. Okay, so that's our integrand, like that's our spherical integrand, right? We converted Cartesian into spherical, and we also had to multiply the Jacobian, which is p squared sine phi. So let's rewrite this a little bit nicer. Okay, squared, 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 that's where I get the 6 from. Phi, 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 becomes sine cubed phi, cosine squared phi, sine theta, square theta, square theta. Okay, that's our new integrand. Perfect. Maybe not perfect, so because it's so big. Alright, it's huge. Ah, damn it. I'm not, okay, so this is our new integrand, right? But let's use the trick that, it's not really much of a trick. Let's use the fact that we only have multiples here. So it's like this rho's times this phi's times this theta. So we can actually split the integral into 3 integrals multiplied by each other instead of going from one integrand to the next integrand to the next integrand, which you can do. It will just take a little bit longer. So I'm going to do the first 2 easy integrals, which is the rho integral and the theta integral. Okay. So rho goes from 1 to 0. It's rho to the power 6 d rho, and that turns into rho to the power 7 over 7, which is equal to 1/7. Okay. Circle this thing because that's part of our answer, right? And then we got another one, and we're going to do the theta integral, which is from 2 pi to 0, and it's a sine squared theta d theta, and that's the exact same thing as 1/2 2 pi 0 1 minus cosine 2 theta. I recommend just burning this into your heart. I mean, the sine squareds, the cosine squareds come up so often. Just remember this formula for sine squared, and if it's cosine squared, it's a positive here. That's the only difference between them. Okay, well, this is going to turn into 1/2 theta, 1/2 theta minus sine 2 theta divided by 2 pi to 0. And what does this equal? Well, this is going to equal to 1/2. Okay, now let's think. 2 pi goes into this. That comes sine 4 pi. Sine 4 pi is 0. Okay. Sine of 0 goes in there. I mean, 0 goes in there. It creates sine of 0. Sine of 0 is also 0. So we can ignore this at all times when evaluating this. So we just got to think about just theta only. Okay. So if then we put the 2 pi here into the theta, it becomes 2 pi. And then we also do the 0. Well, 0 anything is just 0. So all we have to think is just 2 pi times 1/2, which is just pi. Okay, so I already done, like, I did 2 integrals right there. It's, there we go. We just gotta do one more integral, and this is gonna be the harder one. So it goes from what? What does it go from? It goes from pi over 3, this is our phi integral, to 0. And this is sine, not sim, sine cubed phi cosine squared phi d phi. Okay. You're like, oh, dude, this is a hard one. I'm like, calm down. May not be that bad. Okay, that's what I'm saying. Let's make a little box right here. And this box is, I'm going to show you how we're going to convert this. Okay. So we're going to use the fact that 1 equals sine squared phi plus cosine squared phi. Okay, that's true. We all know that. Okay, then sine cubed phi is equal to, let me not skip a step for people here. Sine squared is 1 minus cosine squared phi. And that checks out, right? So then what does sine cubed equal? Well, sine cubed is equal to 1 minus cosine phi squared times sine phi. Okay, that's the same thing. Look at that. So then if I let a, I'll do the other stuff later in a second. So I'm going to rewrite this integral using these trig identities, pi over 3 to 0, and this, remember, that sine cubed is going to now turn into 1 minus cosine squared phi, sine phi, and cosine squared phi still, d phi. And you're like, oh, okay, I think I see what's happening. Now we can use the substitution, right? Now let a equal cosine. Not cosine squared, just cosine. Make your life easier just by picking cosine, okay? dA is equal to negative sine phi d phi. And of course, we have to change our bounds. And I'm going to change our bounds in the box over here just because I want to save some room here. Phi into A. Okay, so if phi is originally pi over 3 and 0, okay, so if we put pi over 3 into phi here, what do we get? We get 1/2. And if we put 0 in there, we get 1. Okay. So now I can transform this integral into 1/2, 1 minus a squared sine phi a squared dA negative sine phi. Oh my god, look at that. The signs go away. And we have an integral purely of one variable. And by the way, you can flip this now, right? You can flip this, and that will also get rid of the negative here, like we did before. So we'll have 1 to 1/2 of, and we're going to factor in the a's into this, a squared minus a4 dA, which as we all know is a cubed divided by 3 is a5 divided by 5. And that is a value from 1 to 1/2. Now, I'm going to evaluate this. It's going to equal to 1/3 minus 1/5, right? 1 just goes in there, and then 1/2. Now, this is the part that's going to get a little trickier. Okay. 1/2 cubed. That's 1/8. 1/8 divided by 3 is 1/24. Okay. 1/2 to the power 5. Okay. Well, that's 1 to the power 5 divided by 2 to the power 5. Okay. And I know 2 to the power 4 is 16. And then 16 times 2, which is 2 to the power 5, is 1 over 32. So we have 1 over 32 divided by 5. Okay, now you get to ask, what is 32 times 5? Okay, well, 30 times 5, 150. 2 times 5 is 10. 150 plus 10 is 160. So this turns into 1 over 160. Okay, now since we're running low on time, I don't want this video to be super long. I'm going to pause it, and I'm just going to give you guys a fraction here. Okay, yeah, so this is 47 over 48, right? And then that's part of our answer. Okay, so remember we had 1/7 pi and 47 over 48. And remember I split it into 3 integrals, and they're all multiples of each other, so we're going to times all those things together. And I like to say answer, just write answer is equal to pi over 7 times 47 over 480. Yeah, and guys, like I wouldn't even bother trying to really do this. I mean, you can if you really want to, but we're just gonna leave it like that. Okay, next problem. Look at this. We have a sphere, and it's above the xy plane and below this cone. And we want to find the volume within those. Now, doesn't that problem look kind of similar to, I believe, this problem? Yeah, like it's nearly identical. Now, notice we used cylindrical coordinates for this one. I would argue that we could have used spherical coordinates for this one. I could argue that we could use cylindrical coordinates, but we're going to use spherical coordinates for this one. Point being is that a lot of times, if you have cones and spheres, you can either do cylindrical or you could use spherical, right? In this case, since it's a 15.8 problem, I am going to use spherical, and let's see how that goes. Okay, so let's start off and just write some facts here. I always like to start off with this. Well, above the xy plane, what does that mean? It means it has to be z is always greater than 0. So we could write z above the xy plane, and below, okay, below this cone. That means that's our top bound, right? Okay. And both of these, both go around 0 to 2 pi for their theta. Okay. Yeah, so where we left off, we said that theta was going to be from 0 to 2 pi, right? Okay, and using this, you could see that rho squared is equal to 4, thus rho is equal to 2, and rho will be from 0 to 2. Okay. Now remember I said we're not going to use cylindrical. But you're like, why do you have a z here? And I'm like, I just read it just because I wanted just to write it. That's why. I mean, there's so it's not that useful, but it was just useful at the moment for just helping visualize something. Okay. This is the equation of a cone, right? And this is the equation of a sphere. Now this tells us that everything is above the xy plane and it's below the cone. Well, that tells us that phi is not going to be dependent on the sphere, but phi is dependent on the cone. That's why I wrote that. So let's turn this z into z squared, just to get rid of the square root. Okay. And I kind of want to do something with this. What do I want to do? Well, I'll tell you what I want to do. I want to insert our, not polar, our spherical coordinates into this. So I'm going to use, what am I going to use? I'm going to use x is equal to rho cosine theta sine phi. I'm going to use y is equal to rho sine theta sine phi. I'm going to use z is equal to rho cosine phi. So if I use this stuff and I put it into this, I'm going to get rho squared cosine squared phi. That's equal to z squared. And then I'm going to get this thing squared and this thing squared. And if they both have they're both going to have rho squared in common. And they're both going to have sine squared phi in common. So I could factor that out. Okay, and then if they both have that in common, then what's left is just cosine squared phi plus, or not cosine squared phi, it's cosine squared theta plus sine squared theta. And everyone knows that this is equal to 1. Okay, look at that. All of this reduces down into rho squared cosine squared phi, which is equal to rho squared sine squared phi. And then all of that even reduces down even a little bit more. You can get rid of the rho squareds because they're on different sides. And then you could write this exactly as 1 is equal to tangent squared phi. Okay, and then let's just think here. Where is tangent equal to 1? Where is tangent equal to 1? Well, it's where sine and cosine equal each other. So it's like right here, it's equal to 1, right? Wherever sine and cosine equal each other. By the way, that's also equal to 1 right here. But let's just focus on pi over 4. Why are we just going to focus on pi over 4? Because remember, the rule always says phi is from 0 to pi, right? It can't be from 0 to 2 pi. It has to be from 0 to phi. So then we got to... Sorry. It's not always that, but that's what phi's maximum limit is. It's from 0 to pi. Okay? So in this case, phi's maximum limit is pi over 4. So we see that phi is from pi to 4 to 0, but I'm going to say we should question it once more. We should question it once more. Why should we question it once more? It's because I have a hunch that this over here has something to kind of do with this, and then this may not be true completely. I know that this is true, but I think there might be a little bit more to it. Okay. So let's just do this in blue now. We say if this is from and right, and rho is equal to z, which is equal to 0, right? Z is equal to 0 right here. That's where I'm getting it from. Which is equal to p cosine phi. Okay. So how would I make this possible, right? Let's just use what we have in common here. Okay, so if z is equal to 0, I'm going to write 0. And if rho is equal to 2, it could be, let's just write rho actually. Okay. So if z is equal to 0, and then 0 is equal to this, right? And I need a angle phi that produces this result, okay? Now, let's think. Okay, if phi, when will this phi turn this thing into 0? No matter what radius this is, this could be any radius. That's why I just wrote it as rho. What angle phi can always produce a 0? It's pi over 2. Okay, and like I know that may have seemed like, oh my god, wait, I thought we just said it's just only this thing, and at the moment it was just that. But we need to always reconsider our other bounds, because when we convert into different coordinate systems, we have to constantly think about all the other little, I want to say, doors that open, because when you change things, other things change, and you need to account for those minor tweaks. So then let's write our actual bounds here. So we have 0 to theta to 2 pi. We know that one, right? And we have rho. We also know this one for sure. Okay. So we got this and this. That's for sure. Okay. Now which one comes first? It's pi over 4. Okay. These are our bounds for integral. And I'm going to go and create another page. And I'm going to do it on another page because we're running out of space. Okay. So let's actually do the integral now. Okay. Yeah, you guys can. That's a little small. Make it bigger. Takes from 2 pi to 0 to pi over 2 to pi over 4. And what was it? I think it was like, what, 2 to 0? Yeah, 2 to 0. And remember, dv is, in this case, just rho squared sine phi dp d phi d theta. And as you guys know, these are multiples. There's nothing that's going to cause us from having to not do the multiple rule. because it's not a plus or minuses here. It's just multiples. So we could write as one integral, which is going to be 2 pi to 0 d theta, which is equal to 2 pi. We got another one, which is from not 1. It's from 2 to 0. It's from 2 to 0. It's rho squared dp, which is 2 to 0, right? Which is 8 over 3. And we got one more integral to do. Let me move my face here. One more to do, and that's pi over 2 to pi over 4 sine theta d theta. We all know that's going to be negative cosine theta pi over 2 to pi over 4. And I always have to factor out a negative when I evaluate, because if I don't, I will always mess it up. That's just me personally. If you don't, good for you. Okay, cosine pi over 2, that's definitely 0. Cosine pi over 4, well, we all know that to be square root 2 over 2. Then we could write this whole answer as square root 2 over 2, because negative times negative. So we're going to take this, this, and this, and we're going to all multiply them, and that is our answer. Okay, so I'll say answer is equal to, let's stop saying answer, because what do we want? We wanted volume. Our volume is equal to 2 pi, 8 over 3, square root 2 over 2. As you can see, the 2's can go away. We get 8 square root 2 pi over 3. That's our final answer. Right there. Okay, there, we're good. Let's do another problem. Okay, so here's the next problem. And yeah, as you can see, I had to move things around because we have to make space. By the way, that's the answer for the last one. Okay. Oh, 15.9 transformations, man. Oh, these types of problems. I might argue that this is one of the harder things in this whole review. Honestly, these problems are just a really huge pain in the ass, and they actually require a bit of thinking. So I don't like to say they're tedious. I don't believe in tedious problems. If it's tedious to you, then maybe you should be doing something else. Okay. So let's start off by just drawing this. The reason why we're going to draw it is because we need to find slope equations for each of the sides of this parallelogram. Okay, so we got -1 to 3. That's -1, that's 3. We got 1, -3, 1, -3. We got 3, 1, just right here. And then we got 1, 5, just right here. So I'll do this in blue so you guys can see it better. Now, by no means is this drawn to scale or even drawn correctly. This is terrible drawing here on my part. Let's just check our points. -1, 3, 1, -3, 3, 3, -1. Damn it. We want 3, -1, which is about here. Okay, so here's our points. This is what it should look like, right? And I'll write 1, 5 here, just so we know. And this is 3, -1. Okay, now what I do is I call this S1, and I call this S3, and I'm going to call this S2, and I'm going to call this S4. Now what you guys should notice is that if you were asked to find equations for each line here, each S, right, you would say, oh, well, S1 and S3 have the same slope because they're both parallel. And you'd say S2 and S4 have the same slope because they're both parallel. And I'm going to say, yes, you are absolutely correct. Let's use that. Okay. So I always do this. I always recommend you do it too, because it's just like Makes your life easier. Why would you not want to make your life easier? So you get S1, S2 plus not S1 plus S2. We have these lines. And now we got to write y equals mx plus b equations for every single s. Okay, S1. Let's think. Starts at 3 and goes all the way down to -3, so its change in y is -6. But what's its change in x? Its change in x is -1 to 1 in the positive direction, so it's going down 6 to the right. Okay, so its slope is -3. Right, 6 divided by 2, -6 divided by 2. And then I don't even need to calculate that for S3. I know it's -3. Okay. And then what is S2? Well, starts at, I'm talking, when I say starts at, it means in the y direction. So it starts at the y height, 3, and goes up to 5. So it's change in y is 2. Starts at 1 here in this case, and then goes to 1. So it goes up 2, and it goes to the right 2. So its slope is just 1, just positive 1. And S2 and S4 share the same slope. Okay, now we need to think about the plus b part. So I'm actually just going to write this now as y equals -3, -3x plus b. And the way we would find b is you pick any point along this line for S1. I did not want to do that. 1 second. There we go. You pick any point along this line. Why don't we pick S1? I mean, why don't we pick where S1 and S2 meet? Why not? And that point is -1, 3. So if we plug that in to find b, we'll get 3 is equal to -3, -1 plus b. And then that's 3 minus 3 is equal to b. Wait, yeah, that's positive 3. It's 3. B is equal to 0. And then we get y is equal to oh god, -3x. I'm not gonna write plus 0. Yeah, and you know what? Like, if you're, big brain, you would have saw that it starts here. So of course its y-intercept is 0. I should have saw that. Wasted some time, but it's fine. We live and learn, right? And let's check this point. If x was at 1, we should be a negative. Yeah, and it would be. So this is the correct slope equation. Okay, let's do it again. Well, y is equal to x. S2, where is S2? Right here. Okay. So y is equal to x plus b. Now you think that's 3. It's not exactly. It may end up being, but like we don't actually know, right? I mean, we weren't given 0, 3, right? I mean, like my drawing, what I'm saying is my drawing's not accurate. That's why I'm always doing the extra algebra, because my drawing's not accurate. Because I'm a human. I can't draw perfectly. Let's find a point on S2. I'm going to use this point again, because why not? -1, 3. 3, -1 plus b. b is equal to 4. So I get y is equal to x plus 4. And let's check that. If x was 1, yes. If x was 1, then y would equal 5, which is that point. So it makes sense. So I'm going to underline all the important things. Okay. Now for S3, we know y is equal to -3x plus b. And let's think about what point we can use. We can use 1, 5, because that is a point on that line. So y equals 5, x equals 1. Okay, and then we can see that b is equal to 5 plus 3, right? 5 plus 3, you would add on the other side, is equal to 8. Y is equal to -3x plus 8. And let's check if this is correct by using this point. So if x was 3, if if x was 3, we would get 3. Okay. Yeah, if x was 3, this would be 9. 9 plus, it would be negative 9 plus 8, which is negative 1. Yeah, so this equation is correct. It does satisfy what we want. And I always check it with the other point. I find B with one point and I check it with the other point in my head because I want to make sure I don't mess this part up. If you mess this part up, everything else will be wrong. So always check it. And let's underline this because that's important. Okay. At S4, y is equal to x plus b. And we'll use point. What point will we use here? We could use 3 comma negative 1. 3 comma negative 1. So y will equal to negative 1. X will equal to 3 plus b. B is equal to negative 4. Y is equal to x minus 4. Let's check this. Okay, if x was, we want to check it with this point. If x was 1, it would be at negative 3. Yep, that's correct. So these are our correct S1, S2, S3, S4 equations that describe this plane in x and y. And you're like, why are we doing this? Well, we need these equations to help with these equations. Other than that, you can't just use these things and just plot in points. I mean, maybe you can, but I think this way is a lot more definite, and it shows that you know what you're doing instead of just fumbling around with points. Okay? So I'm going to shorten all this real quick and make it a little bit smaller. Okay, now here's the fun part, right? We got to use this and plug them into all of these. Because look at this. This is the equation of x, u, and v. That you can't use that to find a equation of u and v. Hence, these equations are purely transformation equations. You cannot use these to graph a u and v plane. Like, you can't use these equations to graph a u and v plane. You can only use these equations to graph a y and x plane. Okay, so what I'm going to do is I'm going to sub these into these. Okay. I did have to shrink everything to make some space. So we'll say for y is equal to negative 3x. What does that turn into? Well, y is equal to 1/4 v minus 3u. And this is negative 3. And what's x equal to? Well, let me erase that real quick. Negative 3/4 u plus v. And I just want to get rid of the fraction here. So I'm going to times everything by 4. Why did that thing happen? Okay, I'm going to times everything by 4 here. So I get v minus 3u, which is equal to negative 3u minus 3v. And as you guys can see, look at this. I mean, we got a negative 3u on that side. We got a negative 3u on that side. They can go away. So v is equal to negative 3v. Thus, hold up for a second. We get, okay, and we got this. This has to be 0. I mean, there's no number that satisfies this. This is equal to 0. V is equal to 0. Okay, that's very nice, right? We get v is equal to 0. That's important. We will underline that. So we did it for this one. Now we need to do it for this one. Okay, so like we said, 1/4 v minus 3u, which is equal to what's plus, and x is equal to 1/4 u plus v plus 4. Let me get rid of the fractions. V minus 3u, which is equal to u plus v plus 16. What do we have in common? We got v's on both sides. And then I'm going to put the u on the other side. We get negative 4u is equal to 16. Thus, u is equal to 16 divided by negative 4. Yes, I actually had to do that, which is negative 4. So we get u is equal to negative 4. And that's our important piece of information that we want to hold on to. We're going to do it again for y. I'm not going to rewrite it. It's right here, right? We want to do it again for that, which is 1/4 u 1/4 v minus 3u which is equal to negative 3 over 4 u plus v plus 8. Okay, so we get, God, why am I messing up? V minus 3u, which is equal to negative 3u minus 3v to the v plus 32. So what I did here is I got rid of the 4's by timesing everything by 4, and then I also factored in the negative 3 into these. That's why it's negative 3 over here. What do we have in common? We got 3u on this side. We got negative 3u on both sides. We can get rid of them. Just write it as v is equal to negative 3v plus 32, which turns into 4v is equal to 32. Thus, v has to be 8. That is an important piece of information. Okay, so if you've seen it so far, we got v is equal to, we have all these like nice little pieces of information, and I would argue that it looks like this parallelogram is going to turn into a rectangle. Oh, isn't that nice? So now we get to transform y equals x minus 4. What are we going to use this and turn it into? Well, y is equal to 1/4 v, not u. Why am I writing u? See, that's why I hate u substitutions, because it's like you end up writing u 100 times over. Like, pick different variables, or it sticks in your head too much. 1/4. Okay, so let's times everything by 4 again. V minus 3u, which is equal to u plus v minus 16. Don't forget to times these guys by 4. When you times everything by 4, they still need to be times by 4. We have v on both sides, so we get negative 3u, which is equal to u minus 16, which is equal to negative 4, which is equal to negative 16. Negative 4u, which is equal to negative 16. Thus, u has to equal to 4. Okay, so I'm going to shrink this whole table right here, and I'm going to draw the plane. Okay, so I have a v and u plane. Now I'm going to call v vertical, and I'm going to call u horizontal here. Like, this is going to be a rectangle. What does v equals 0 mean? Well, it means this whole line right here. It's like the L that's v equals 0. What does v equal 8 mean? It means right? And then what does u equals negative 4 means? It means this right here. Or let me write this nicer. I'm going to write 8, 4. So I'll make this nicer in a second. And then we got that is equal to u 4. U is equal to 4 here. So then we have this, like, we just want the area that overlaps, which is this area in the middle. Okay. And I'll give you these points because that's what you want to know, right? Well, this is where we see negative 4, 8, and this is what we call 4, 8. And remember, it's u, v, right? These points are u, v. And this one is, what is it? Now, you actually don't need to label these points. I'm just doing it purely for the viewer's sake. This would be 4, 0. And this one is 4, 0. The other one's negative 4, 0. Yep. Okay. And everyone loves integrating rectangles. So we have these new bounds. Oh, let's transform. I'm gonna write this as, one second. I'm gonna write this as f of x dA r, and we're gonna transform this into. Now, everyone in the book, like everyone that reads the book, realizes that they like to call this region S. So I will call it S2. So we'll call it S, and this is gonna be a function of u and v, and remember, we have to have a Jacobian, right? XX. x comma y, duv, du, duv. Okay, so this is our transformation of planes, which transforms our integration. Okay. Now I'll set up our new integrand over here. Okay, so I do not want to do that. Our integrand once was 4x plus 8y. How can we turn this into a function of u and v? Well, we can use our transformation equations, which nicely they provided. If they didn't provide this, we would have to find them ourselves. We would have to find them kind of a similar way, unfortunately. So this would be like doing this thing like twice, honestly, if they didn't provide that. Also, sometimes you can, just they luckily give you something that's nice and it kind of see it in integrand. But for this case, things were given and this problem works out pretty simply. So this is equal to 4x. Well, 4x, it's just u plus v, right? Because here's a 4. So if you times x by 4, you get rid of the 4 here and just get u plus v. And you got 8 here. So 8y is just 2v minus 3u. And 2v, we'll write it as plus 2v. And 2 times negative 3u is negative 6u. So our new integrand is just going to be 3v minus 5u. That's our new integrand. But it's not fully complete. We need a Jacobian. I'm just write Jacobian. What is our Jacobian? Well, we'll find it right now. Now d, the partial of x, a function of x and y, partial of a function of u and v. We can create a determinant. Or integrate x with respect to u, x with respect to v, y with respect to u, y with respect to v. Well, that turns into, it all can turn into, I'll write it, let me move something real quick. That's our formula, right? I'm gonna write right below. So x with respect to u. So we need to integrate x, not integrate, we need to differentiate x with respect to u. It's just u. The derivative of u is just 1. So it's 1 times 1/4. The derivative of the derivative of x with respect to v, where it's just v right here, is just 1 and 1 times 1/4. Okay, the derivative of y with respect to u, and it's just u, it's just going to be negative 3/4. And similarly with v, it's just going to be 1/4. So if you don't know how to do these, what you do is you multiply these guys, like you always go diagonal, diagonal, and diagonal minus diagonal. So 1/4 times 1/4, 1/16, 1/16 minus 1/4 times negative 3/4. Well, what are these? This is negative 3/16. All right, and then we get positive 4/16, which is equal to 1/4. Our Jacobian's 1/4. Okay, so our integral is actually, so I put du dv. So let's write a region of S real quick before we integrate. I'm going to write it over here. Okay, S. That is a terrible looking set. Where u and v. Okay, what is u? U goes from negative 4 to 4. What does v go? V goes from 0 to 8. Okay. So I'm actually going to switch the order here. It's totally Totally doable. You can switch the order because none of these are functions, okay? So I'm going to write our new integral, which is from 4 to negative 4, from 8 to 0. Okay, and remember, this is our new integrand, and this is our Jacobian, so it's Jacobian times our new integrand, which is our new integrand. Sorry if that's confusing. It'll make sense in a second. So I'm going to write the Jacobian on the outside. The Jacobian is 1/4, okay? So see that 1/4 that goes over here? And then we get 3v minus 5u. And what's the order of integration? It's dv du. Why did I change the order? It's because I didn't want to have a negative 4 term that would expand this first expand the first setup here. So that's the only reason why I did that. And I'm gonna go on to the next page and do this. So let's rewrite everything, unfortunately. Never enough space, right? 1/4, 1/4, 4, negative 4, 8, 0. I believe it was what, 3v, right? 3v, 5u. Okay, so if we integrate first with respect to v, from 8 to 0, we'll do that. 5u dv. Forgive that really ugly looking 5. I mean, that's a sin, how bad it looks. 3v squared minus, it's 5uv. Okay, I wrote it as 5vu here. Same thing, 8 to 0. Oh, now everything's lagging on my part. Okay, I'm only going to evaluate our v terms, okay? That's all I'm going to do. And luckily, v is in every term here. So when v is equal to 0, we don't have to worry about this whole thing, right? Okay, let's think. So 3/2, 8 squared, because v will become 8. 64 minus, and then 5v, 5 times, oh, do not want to do that. 5 times v is 40u. What does this turn into? Well, we can first think about 64 divided by 2, which is 32. 32 times 3 is 96, right? So we get 96 minus 40u. So that's our next integrand, and will lead into our next integral. I'll put an arrow. And then what's our next integral? Well, it's going to be from 4 to negative 4, 1/4, 96 minus 40u to u, 96. Let's not forget our 1/4, 1/4, 96u minus 20u squared, all evaluated from 4 to negative 4. Let's see what this can turn into. Well, this can turn into, okay, well, okay, we got 96. I'm just gonna actually just do it raw here. 96 times 4 minus 20. 4 squared is 16. Let's write it like that. We'll have minus 96 times negative 4. Now, why am I not just multiplying these out right now? It's because there's a negative 4. I mean, there's a 1/4 out here, and it'll help kind of get rid of things. Also, if you notice when there's a, oh, do not want to do that. When there's a 4 and a negative 4 here, and these are not of the same, they're not even, and like if it was even and even, I would be able just to kind of ignore this, but since it's odd and even powers, I actually do need to kind of go out the whole way here. So I will actually do everything, but then it's going to simplify nicely in a second. Well, minus 20 and negative 4 squared is still 16. So let's write all of this. Okay. Okay. What do you see? What do you see? What do I see? Well, I see that we have a negative 20 times 16 over here, and then we'll have a negative and a negative, that will be a positive 20 over 16, 20 times 16. I believe that these can cancel each other. Okay. What do I see? I see a negative here and a negative here. That will be a positive, right? But then I see a positive over here. So if they're both positives, then that's just 2 times 96 times 4, all divided by 1/4. So it'll be array is 96 times 4 times 2 over 4. Oh, not over 4. Give me a second. Let me erase that bracket. It's 1/4. 96 times 4 times 2. And yes, the 4's go away. Then we get 96 times 2. 90 times 2 is 180. 6 times 2 is 12. 180 plus 12, 192. That is our answer. A lot of work, huh? A lot of work just for 192. Okay, let's do another problem. Okay, so this next problem, they don't give us a transformation equation, and they really don't give that much. They tell you the ellipse. That's about it. Now, I'm going to tell you what I would want to do, but you can't do this. You cannot do this, okay? 9x squared plus 4y squared is equal to 1. You cannot just put sine of 1 and then integrate. That won't work, okay? Like, as much as I would love that to be true, it's not. We have to go through some misery and pain first before we can actually get the answer. Okay, so let me help establish that misery and pain real quick. We need a u and a v. We need a u and a v. You cannot just say u is equal to 9x squared plus 4y squared, because then you'd have no v. Well, we can kind of do something a little bit close to that. Maybe we could say that u is equal to, maybe we could turn this into u squared plus v squared, right? I think we could do that. We can't just say u or v is equal to that whole thing, but maybe we could turn it into u squared plus v squared is equal to that. And if that's true, then what does u squared have to be? Well, then u squared has to be, by the way, this is all equal to 1. I'm finding the bound first here. Then u has to be equal to 3x. And v has to be equal to 2y. Right? Because if u, let's just check. If u was squared here, it would be 9x squared. And if v was squared, it would be 4y squared, which is exactly that. That's exactly what we want. There we go. We found our transformation equations. We have transformed from the x and y into the u and v. Now, let's go one more step farther, because we could just we could, go down this route into the u and v plane, but I think we should hold back for one more second and think about what this looks like. I think this looks a lot of like a circle, it looks almost identical. Well, it is the u and v. This would be a circle in the u and v plane. And if it's a circle in the u and v plane, then it's a circle in the r and theta plane. And if it's a circle in the r and theta plane, we know exactly how to deal with that. But before we exactly do that, we want to realize that, what does this question ask? Where r is the region in the first quadrant. Okay, so if it's in the first quadrant only, it's a quarter of a circle. Okay. So we got u. It's a circle in the v and u plane, but it's only a quarter circle. Okay, and then we know exactly how to describe this using r and theta, where r is from 0 to 1, and theta is from 0 over 2. Okay, right? 0 to pi over 2. Yeah, so this is our final bounds. This is all we need. I'm going to shrink everything just so we have more space for later. Okay, so we found our final bounds, we find our transformation equations, but we actually now need to do some calculus. But before we do that calculus, let's just make our life a little bit easier and find our integrand. We go from sine of 9x squared By the way, you don't need to do this. This is just for the sake of showing you guys. Right? dA, let me write it as dx dy for the sake of what I'm about to show you guys. Which is the same thing as sine u squared v squared du dv, which transforms into sine of r squared r dr d theta. Why did I do this? Because I want to show you guys something that's very important to realize. When we make this transformation, you have to realize that you have to have your Jacobian here. So even though we transform the x and y into the r and theta, you actually had an intermediate step, which is the u and v, and your Jacobian that you found for that middle transformation will carry along. Okay, it's going to carry along. Let me show you. Well, let's first find our Jacobian. By the way, we actually have two Jacobians here. It's the xy uv one and it's the r one. But we already know this one because like you've just memorized that Jacobian. xu, xv, yu, yv. I don't know what these are yet. I just have to do minor little algebra here. X is equal to u over 3. V is equal to, not v, y is equal to v over 2, right? Then we get, so if we take the derivatives of both of these things with respect to those variables in this order, we'll get 1/3, 0, 0, and 1/2. Do not want to make that random line, which is equal to 1/6. Okay. So then now your final integration, not integration, your finer, that's not a word. Your final integral is 1/6 pi over 2, 0, 1 to 0, sine r squared r d theta. And yes, this is true. Like I was saying, that's why it's so important. Your Jacobian from x and y to u to v carries along, even though it's not in u and v anymore and it's in r and theta. It carries along, okay? And I have proof of this because you guys done it last section for spherical. There's a reason why it's rho squared sine phi. There's a reason why that's your Jacobian for cylindrical into spherical. It's the same concept. It's just you don't realize it because you haven't actually solved it. They have just given it to you. In this case, we have to solve it, okay? Let's do our first integral. By the way, look at this. There's no theta function, so we could just do our first integral as pi over 2, 1/6, 0 d theta, which is pi over 2 times 1/6, which is pi over 12. Remember, we can use the multiple rule for integrals. Okay, now we actually got to do some Calc 2 integration here. Okay, well, let's just pick. We got to make a substitution. I mean, you already seen this one before. I'm gonna let tritant be our variable because I don't like u's. Where tritant is r squared, d tritant is 2r dr, and we transformed from r into tritant. R was 1 and 0, and if you put 1 into here and 0 into here, it's the exact same balance. So this turns into 1 to 0. R sine tritant d tritant over 2r. Your r's can go away. Get 1/2 cosine, negative 1/2 cosine tritant 1 to 0. The same thing as cosine negative 1/2 cosine 1 minus 1, which is the same thing as 1/2 1 minus cosine 1. We just have to make it look better because, you know, that's unacceptable to write it this way. On a test, I always write it that way just to piss off the graders and my teachers. But yes, when you're doing homework, write it this way because it looks better. Okay, so in the end, what do we need to do? We need to multiply pi over 12 times 1/2 1 minus cosine 1, which is the same thing as pi over 24 cosine 1 minus 1. No, it's 1 minus cosine 1. That is our final answer. Okay, so vector fields now, right? Oh, God, right. But I'm not gonna actually, like, we could, if we really want to know, we could actually grab all these fields and then do it that way. But what we should try to do is ask ourselves questions about what we think the field would look like, and then eliminate choices of what we definitely know it's not going to look like. And that's how we can most effectively answer questions 15 to 18 here. Okay, so we want to match the field with the correct vector. Okay. Number 15, it says we have a field with an I, a J, and a K component. Now, if we look at the scalar right next to the I, J, and K, you know, I is 1, J is 2, and K is 3, right? That's their scalar multiple. So what that means is that going in the X direction, it won't be as strong as if it's going in the Z direction, right? And if it's going, and it should be also more strong, it should be the strongest in the Z direction. It should be the second strongest in the Y direction. It should be the weakest in the X direction. So if we had to think about that, let me just restart my tablet real quick. Okay, now my tablet's working. So this is just for number 15. I'm just gonna think about this just for number 15 here. The vector field for number 15. So I'm gonna use a blue. So if we start the origin in the X direction, it should be like just a little thing, right? A little scalar, just 1. And in the J direction or in the Y direction, whatever you want to call it, it should be a bigger scalar. Call it 2. And then in the Z direction, the K direction, again, they're synopsis with each other. It should be the largest. Be like that. So if you had to think about this, what does this mean? Well, I'm going to draw the resultant between the X and in the X and Y plane, between these two. It would look kind of like that. Like this is what, just in the X and Y plane, what this resultant would look like. Well, if I drew a resultant in this Z and Y plane, it would kind of look like this, right? Where this would be the main contributing vector, and this would be the lower primary contributing vector. Now, if we're to draw all of these, so like if we're directly at the dot, it would be like a line that's coming at us. It would be vectors coming at us, where primarily it'd be coming up at us. So if I ask myself a question, it's not this field. This field is like definitely not it, because it's going in all different directions, right? This field, not it either. I mean, this shows that there's a negative Z component, right? There's a negative Z and a negative Z. This one has a positive Z, but it looks like it's all spiraling from the same point. Like it's like as if it was like a water fountain shooting out. I'm gonna argue it's this one. And in fact, if you think about it, let's look. This is the x direction, right? It doesn't look like there's that much contribution from the x side. It looks like there's some more contribution from the y side. It looks like there's the most contribution from the z, which is exactly what with this vector f here with its I, j, and k components describes. So number 15, we can call it, we'll match it with plot for, oh no, did not want to do that. Oh, something messed up on my screen. Forgive that mistake. We'll call it, why is everything messing up on my tablet? It's number 4. Okay. Okay, let's continue. Number 16. I is 1, j is 2, and k is z. What does that even mean? Okay, well, it means that you're going to have some fixed values always in the x and y direction, or like you could say in the I and j direction. You're always going to have some fixed values. It will actually look very similar to like this, except z is your scalar for k, which means it could look like anything. It could look like anything in the k/z direction. It just depends on whatever z is. So we need to think about a vector field that gives it complete independence for its vector in the z direction, its subvector in the z/k direction. Okay. Well, obviously it's not this one because we just eliminated this one, and I could tell you it's not going to be this one. I mean, right? This is like definitely not this one. Okay, now we got to think between these two, right? Let's ask another question. Let's think about it this way. If I mean not if z, if we had to think about it at 0.111, what would that be? So that 0.111 here, it'd be like that. This 0.111 in this vector field. Or you could think about it in the origin, right? Like, let's just think about any point in the origin. Maybe that would be easier. Like right here, like the middle, the exact middle. If you were to ask a question, would this fit this solution? Would this be a solution to that question that I ask? And what I mean specifically, okay, well, look, I is still going 1. J is still going 2. But then Z is whatever Z's coordinate is at that moment. And if Z is equal to 0, then Z has no contribution. And if Z is positive, then Z has a positive contribution. And if Z is negative, then Z has a negative contribution. And that's not what this graph says. This graph says Z is always positive. This graph says Z is always positive. This graph says Z could be whatever it wants, but it also says X can be whatever it wants and Y could be whatever it wants. So it's not this one, it's not this one, it's not this one. It has to be I. It's plot 1. Okay. Let's go with the next. All right, let's think about number 17. X and Y and 3. That's our vector. Okay. So in the I direction, X is whatever it wants to be. In the J direction, Y is whatever it wants to be. But then Z is always 3. If Z is always 3, we have to think about something that can provide an answer to this question. We ask, what graph shows that Z is always going to be 3? Not this one, because we answered it earlier. This one says that Z will equal 0, and if Z is equal to 0, we said Z is always equal to 3, so it's definitely not this one. Now, is it this one? No, look, Z is going in a positive, a negative direction. It's like, it can't be this one. It has to be number 3, because Z is always acting with a scalar of 3. 3 in the positive direction, too. So it's number 3. Okay. Number 18. Okay, so we did eliminate these 3 already, so, I mean, just by that, you already know it's this one. But I want you to actually think about this, because this is actually important vector field to kind of remember, just because you'll see it somewhere else in physics later, maybe. Maybe, yeah, you will. Think about this right here as if this was a explosion, right? If you had to describe the shrapnel flying out of a explosion, this would be the vector field you would use, right? And then you'd say, oh, how can I describe the piece of an object flying from that explosion, the shrapnel? How can I describe the shrapnel's flight path with a vector? Well, you'd say it's whatever it wants to be, right? It's going to blast off whichever force is the strongest, and that shows you that's X, Y, and Z, because it's saying that, hey, if there's an explosion right here, it's going to go flying here, piece flying there, piece flying there, piece flying there. It's like wherever the forces are just pushing it, and the forces are pushing it all in equal directions, where it's all the same scalar. Yeah, so let's just call it right there, right? I mean, with that explanation, I'm going to say 18 is number 4. And also, if you really, I mean, it's the only one that makes sense, right? For this, because this is the only one where it's, you think about it, can describe this, right? While these ones definitely cannot describe this vector. For this next problem, we're not given these graphs, unfortunately, so we actually got to find a vector equation that describes this. Okay. So we could say that F is equal to del F, which would mean this would imply this is a conservative vector field. And if you don't know what del F means, it means the derivative of F with respect to x and y. And I say only with x and y because these are our only two variables. If you had x, y, and z, it would be del F is fx, comma, fy, comma, fz. The point. So if we take the derivative of f with respect to x, we're going to see it. That's just x. Because there's a 1.5 out here, the 2's will go away. Okay. Now, if we take the derivative of f with respect to y, it will just be negative y. Okay. So, just thinking about this already, you could imagine that this vector field will almost kind of look something like this, except there's going to be a negative here, and there's no z component. Okay. So let's actually just construct the table. I always like to construct the table, because it's how I can think best about it. I'm going to draw a table. xy, and this will be df, dx, df, dy, which is just another way of writing fx, fy, and specifically, that is x and negative y, okay? So you could also say that this is x and this is negative y. So whatever x and y is, we'll find their components here, and then we could graph our vector. Okay, now you're like, what points do I pick? Well, there's a trick to it, really. So you make a rectangle, and you just pick simple points, just things like 1s and 0s. So you have a 1 here, 1, 1. This would be 1, negative 1, and this would be 0, 1. This would be negative 1, 0, negative 1, negative 1, 1, negative 1, 0, negative 1. This is 1, 1. No. 1, 0. Yeah. The reason why I pick these points is because it just makes it's the simplest way just to plug in here and define these values, and then you can graph your vector. And you'll see what I mean in a second here. So I'm actually just going to pick 4 points here. If you really want to get a really good drawing, you pick more points, and you keep doing larger, like one rectangle, and then a larger rectangle around it, and a larger rectangle, and then you'll create a really nice looking vector field. But for the sake of this, we're just going to pick the outside points like this. Okay. So if we start at 1, 0, and we go to 1, 1, and then we go to 0, 1. I'm just completing the round. We go to negative 1, negative 1, 1, and we go to negative 1, 1, negative 1, 0. Now this table is a little too small. I gotta make space here real quick. Okay, so now I got more space. Negative 1, 0, negative 1, negative 1, 0, -1, and 1, -1. Okay, so like I said, this is only x, whatever x is equal to. So look, it's going to be 1, 1, 0, 0. We're just going to rewrite the x coordinate. That's all it is. 1, 0, 1, 0, -1, -1, -1, 0, 1. That's all it is. Okay. But this is whatever the negative y coordinate, whatever the y coordinate is, times -1. So this is going to be 0, -1, -1. Look, here, 0 is the y. 1 is the y. We get -1. Because remember, this is our vector. So that's the only kind of confusing part, really. Sometimes if you get like a crappy function of f, they'll like switch it and it'll be like -y and positive x here, and then you got to really think about it and take your time. But for this sake, it's just this, right? So you just take the opposite value of y. Whatever y is, it's just the opposite. Okay, so this is enough. This is totally enough information. And when graphing this, like let's say you want to graph at 0.10, so you go to 0.10, which is right here, and then you think, what is df dx, and what is df dy? So df dx says go to 0.10, go 1 in the x direction, and then don't go in the y direction. So this is just like this. And then, for example, 1, 1, you go to 0.11, it says go 1 in the x direction, and then go 1 in the negative y direction, right? So then that's it. So I'll draw it now. And I'm going to draw it using blue so you guys can see it better. Like this. And it'll be like this. Now, I did kind of show you guys here, but remember it's... And what is that? What is that little green right there? That little... Or I'll try to zoom in for you guys. 0%. Oh. And... Oh. Here we go. Right? That is df dy, and this is df dx. That's how you can think about it. And then the blue is just the resultant vector between those two. Okay. And if we were to, now I'm going to zoom out now because I need to see the other points. Okay, so now we're back to where we want to be. Okay, so if we're at 0.01, what does it say? It says to stay where you are in x and go down. If we're at -1, 1, if we're over here, what do we want to do? We want to go negative x direction and then go down. That's kind of an ugly vector. Let me redraw it. Do like this. And if we're at this point, what do we want to do? We want to go to the left and then stay. Similarly, right here, what do we want to do? We want to stay. No, we don't want to stay. At -1, -1. We want to go to the left 1. We want to go up 1. Now let me guess what 0, -1 is. Well, 0, -1. Look at that. Same thing. This is what our vector field looks like. So if you're to really add a lot of points, you could get a really nice drawing. But for our sake, this is a good enough drawing. This tells us a lot of information. That's our answer. And notice the symmetry in this vector field. That's maybe something to take notice to. Okay, this next section will be my favorite part of the whole class, actually, is line integrals. And there's like 3 types of line integrals. Now, the book doesn't really talk about them. Nobody actually really says there's 3 types besides me. I'm the one that really says that. And I'll explain what I mean in a second. So if you're given this line integral, dx, I like to say there's the Cartesian case where you should try to keep your line integral in Cartesian because it's just easier. You don't need to find a time conversion. You don't need to find a common variable because you're Cartesian. Like you could find it all using x, or you could find it all using y. In this case, we could actually use x or y and convert and do this whole integral in both cases and get the same answer. And I will do that. But let me just talk about the other cases first. Okay, and then you get this type of integral where it's a dx, a dy, and a dz, and it's a bunch of line segments. And then this is where I recommend that you actually use a vector equation, and I'll write that vector equation later on, and then you use that vector equation to transform this integral from x, y, and z into functions of time. Okay. There's another case you could do. This is where you have the f dot drs, where it's already where you got x, y, and t, and what you need to do is you need to convert your force, your vector f, into a function of time using r of t, and I'll explain more on that in a second. But you do have one more type of case. It's where you have a ds, and we can use ds as the square root of dx dy, not dx dy, dx dt squared plus dy dt squared. So it's kind of like a Pythagorean theorem for differentials, if that makes any sense. It'll certainly look kind of like that when I actually do it, but this is what I mean by there's like 3 cases for these simple line integrals. There's more complicated line integrals, but we won't be doing any of those because it's above our pay grade. So let's do number 9 first. Okay. So, like I said, let's just keep this guy in Cartesian, right? And I'm going to do it using x as our parameterization and y as our parameterization, and both will have both create the same answer. Okay. And maybe you guys want me to draw a picture, but I'm not going to do it in red. We'll do it in black. You guys want me to draw a picture first? And yes, I'm going to put x and y. Notice I switched x here and y over here because I know what y equals x cubed is. So I could assume that this is what this graph looks like. If we just change our variable order, I mean, it's, all you did is just turn your paper. If you're doing this in paper, just turn your paper, right? Or if you're doing this in tablet, just turn your tablet. This point would be -1, and this point would be 1. So, I mean, this is exactly how it would look like. So, if we have, I'm going to ask you a few questions here, right? If this is our change in x, this is our change in y, how can we describe this, right? Well, if we choose x to be our, I'm going to call it our main variable for our parameterization, it's the easiest case. So if we let x equal, I'm not going to say equal, let x, sorry, give me a second. Let x be the main variable. And if you let x be the main variable, then you have to find bounds for x. What is our bounds for x? It goes from -1 to 1. So that's our bounds for x. So right, x goes from 0, not 0, from -1 to 1. But then you need a differential dx. Well, you already have it. I mean, you have it. It's dx. dx is equal to dx. I mean, that's all it is. So now I'm not even kidding. This is your line integral. This is all it is. 1 to -1 e to the x dx. It's as simple as that. Like this problem, you may think you need to do more, but I'll show you. You're gonna get the same answer if you do it both ways. This is e to the x, 1 to the -x, which is e minus this. This is e to the -1. Okay. I mean, you could that's like 2.7 minus 1 divided by 2.7 if you want to actually get a decimal here. Okay, now let's do it as with y being our main variable here. Put me right here. If we let y be the main variable, what happens? Well, what does y change from? It changes from -1 to 1, okay. Why do I keep writing zeros? It's y goes from -1 to 1. But x is equal to y cubed. Well, what does that mean? Well, Oh, I mean, we could still use the fact that dx then is equal to 3y squared dy. Okay, so I'm just going to do a little bit of an integral transformation. We get c e to the x dx. That's going to turn into 1 to negative 1 e to the y cubed. And dx is equal to what? Oh, look at that. And you're like, oh, I want to do a u sub. And I'll tell you, why don't you do an x sub? You already know what x is equal to. And then look at that. I'm not even kidding. You could change, you could do a u sub if you want. You're going to say you're going to get the exact same thing. And just instead of x's, you would have u's. And like I said, we found this earlier. Yeah, so I mean, look at that, guys. Like, you get the same answer. That's why I talked about. Like, I want to talk about this specific case because it's like it's a line integral, but really just it's a Cartesian line integral. You don't have to try to find uh, a position vector using r and t, right? Just use x and y, and you're going to be fine. Now, these cases are kind of rare. I mean, they also sometimes require some thinking if it's not as nice of a problem like this one. But hey, I mean, it worked, right? Let's do this other problem. Okay, so I just made some room real quick. Okay, this is the problem where I think we should actually try to use our vector function and, you know, convert everything to a function of t. Okay, I will draw this picture. Actually, I can't really draw this picture because it's 3D and it's kind of hard to draw like these lines in 3D. So I'm gonna just write the vector function. Like, honestly, I'm not even kidding. If I draw it, it may confuse some more people. This is our vector function. You maybe have seen this from Calc 3. Not maybe, you definitely have. This thing was like used like every day in Calc 3. Okay, so RO. Oh, yeah, we have two paths, right? We have from, not two paths, we have one path, but like we have a C1 and a C2. C1 is this coordinate to this coordinate, and this coordinate to this coordinate. So I'll write C1, C2, and it goes from 0, 0, 0 to 1, 0, 1. This goes from 1, 0, 1 to 0, 1, 2. Okay. Now you'll see why that's important in a second. And let me just actually move all this junk down here. Okay, so let's find R of O in both of these cases. What is it going to equal? R of, not R of O, R sub O, original point, original vector, 0, 0, 0, 1, 0, 1. Okay, what's the next thing we want to find? We want to find V. V is our change in vector here. So we have a change in vectors, a change in position. So this is, I don't actually always do the subtraction here because I like to ask myself questions and have the questions do the subtraction for me. What I mean by that is I say, hey, we're at the origin and we go to this point 1, 0, 1. What's the change in 1? What's the change in x? It's 1. What's the change in y? Oh, it doesn't change. What's the change in z? It does go up 1. Similar. Okay, what's the change in x? It goes from 1 to 0. Okay, well then it's going down. It's going down, okay? 0 to 1. What's the change here? And y? It's going up 1. 1 to 2. Okay, it's going up 1. Okay, these are our vectors. These are our change vectors. Now I want to give you guys a tip here how to memorize this formula. Okay, R is a position vector. R. So if you think about this in like terms of units, right? R would be in meters. RO would also be in meters. But then let's just like literally V. You think of V as in velocity, right? And velocity is in meters a second. But then T is always in seconds. So then if you see you have time times velocity, wouldn't you just have meters divided by seconds times seconds? So then you would have just meters. And then exactly, yeah, that's how you know that this is a position function. A position function. And I don't know if maybe like this clicked in everyone's head, but doesn't this look exactly like this? Or maybe exactly like this? It's almost like that's kind of where we get this type of, information from. That's almost where we get our physics from, right? Using these equations. They all relate. Okay. Now, besides the point, let's just write R. And by the way, this is always true. I know this may seem weird. I had originally a question on it, but there's like there's a 1 here. It's not a 2, it's not a 3, it's a 1. As long as it's going to be 1. Give me a second, my screen's delay. Sorry about that, there's some screen delay. Okay, I fixed it now. Now, like I was saying, what's the number in front of this t? It's 1. For that reason, t is always going to be from 0 to 1. So here we go. So now we can just find our vector r. That's what we want to do. Well, our vector r is going to be 0, 0, 0, 1, 0, 0, 1, plus, plus, t, 1, 0, 1, t, negative 1, 1. And all of that is simply equal to t, 0, t. And all of that is simply equal to 1 minus t, t, and 1 plus t. Okay, right? And like this is true. I mean, this is x, y, z, and this is x, y, z. Now, please note that these are, different c's, right? So it's not like x is equal to t and x is also equal to 1 minus t. It's just, in this case, x is equal to t, and in this case, x is equal to 1 minus t. The x that looks like a y, yeah, now it looks like an x. Okay. So we're gonna use these x's and use these y and z's, and they're the same thing as this t and 0 and t. I'm going to swap them in this equation, in this integral, and change the integrand all into one function of t. Okay? But before we do that, why don't we find our differentials? dx. What is dx? If dx is t, if x is t, dx is dt. If y is 0, okay, dy is equal to 0. Oh, damn, I need more space. If z is t, then dz is equal to dt. Okay. If x is 1 minus t, then dx is negative dt in this case. And if y is equal to t, then dy is equal to dt. And if z is equal to 1 plus t, then dz is equal to dt. Okay. So we're going to use those facts, and we're going to change this one integral into two different integrals over two different c's. Okay. So I'll show you what it looks like. And by the way, we're only going to do, like I say, one integral at a time, right? Because there's no point in trying to convert this all into one giant integral, because it's going to get super confusing and super messy. So for C1, we're going to have 1 to 0. Okay, y, this is y plus z. Y plus z, well, that's t plus t, which is 2t. Dx is what? Dx is dt. Okay, x plus z. X is, what is x here? X is t. Did I mess this one up? No. Y. Yeah, this is y and z. My bad. Messed up the little. Y and z. Well, y and z is 0 plus t, which is t. Oh. T dt. X plus z is t and t, which is 2t. Dy is dt. Oh, dy is 0. Look at that. X plus y, x is t, y is 0. It's just t times dz is dt. It's t dt. I'm going to make this look a little bit better. 1, 0, 2t dt, which is equal to t squared over 1 to 0, which is equal to 1. All of that giant integral turned into this little one. That's the power of these line integrals. The power of finding a common variable. Is it expands and then it shrinks. It's kind of a fun thing to watch. Okay, for path 2, not path 2, for C2. Well, we got y plus z. Well, y is t, z is 1 plus t, so that's t plus 1 plus t, which is 1 plus 2t. And this is dx. Dx is negative dt. Okay, and then we got x plus z, which is 1 minus t plus 1 plus t. Looks like that t goes away. And looks like the 1 stays. So it's 2 dy. dy is dt. 2 dt. Okay, we got x plus y. X is 1 minus t. Y is t. Looks like the t's go away. It's 1 dz. dz is dt. 1 dt. What does this turn into? It turns into 1 to 0. 3 minus 1 minus 2 t dt. Remember there's a negative dt here. Why is it a negative dt? Because there's a dx here. And we found dx to be negative dt because x was 1 minus d. So a lot of things going on. Just take your time when you're actually doing it. It should make sense. I'm going to write this one more time. It's 2 to the 1 minus t dt. Which, as you guys know, is equal to t 2t minus t squared 1 to 0, which is equal to 2. 1 minus 1 half, which is equal to 1 minus 1 half is 1 half. 1 half times 2 is 1. Oh, look at that. Our final answer is, let me make this. This is equal to I1. This is equal to I2. So our final answer is the sum of I, which is equal to 1. 1 plus 1, which is equal to 2. That's our final answer. All of that, so the calculus isn't that hard in this case. It's just transforming it into usable calculus is the hard part. There's a lot of things going on. This is the most important part. Almost all of your credit will mostly come from this part, in my opinion, or at least it should. So take your time when doing this because it's easy to miss negative. Okay, these next few line integrals are actually my favorite types of problems because it's integral f dot dr, and there's actually ways to do these really fast. It's called my way. I hate writing things in I, J, K, component. Don't do that. It's AIDS. That's terrible. I don't know why you'd ever do that to yourself. Let's just find f of t and start from there. Well, why am I doing it in red? F of t. Remember from last time, we can use r of t and sub it into each little x, each little y, where x is t cubed and y is t squared. So stop writing in IJK form and start using column vectors. It's a lot better way to write your vectors. Okay, so x. So the first part, xy squared. Let me just write f real quick so I don't confuse anyone. F is originally xy squared, negative x squared. And then this is going to be the same thing as t cubed times t squared minus t cubed. Right, or minus t cubed squared. There we go. So this is equal to t, well, that becomes t4, this becomes t7, that becomes negative t6. There we go, we found f of t. And that's all, it looks a lot simpler too when you write it like this. We also want to know dr. So dr is going to be 3t squared. I don't know why my square didn't. dt. Right, this is r prime of t. I just put the differential dt on the other side. I took the derivative of this one, which is 3t squared, took the derivative of this one, which is 2t. So then we got to ask, what is f dot dr? Well, f dot dr is the same thing as t to the power 7, negative t to the 6, dotted with 3t squared, dt, which I got to move my cam down here now, which just literally just go right across. That's why I do it this way. Just 3t4 and negative 2t7 dt. Real quick, I messed up. I see the mess. Let me fix it. It's 7. Power of 7 times power 2 is power 9. Yeah, there we go. Now that's correct. So now we just got to integrate that vector. So it was originally cf dot dr, and now it's going to be from 1 to 0 of 3t9 minus 3t. Why do I keep writing squared? 3t to the power 9 minus 2t to the power 7 dt, which is equal to 310t10 minus 2t8 over 8. Yeah, I will get rid of that 1/8. I mean 2/8 and turn it to 1/4, which is equal to 3/10 minus 1/4, which if we think about this is 6. We want to make our common denominator 20, so that'd be 6. On the other side, this would be 5. That's our answer. There we go. That's why I like doing it this way, because look at that. I mean, it's so clean if you do it this way. Look at that. I mean, you could do line integrals in like less than 3 minutes. Like, I could do them faster if I wasn't explaining everything. But, I mean, when you write your vectors like this, instead of doing I hat, j hat, k hat, and plussing, and that's just terrible. I mean, I hate that notation so much. Do this column notation, and you can just fly by. Okay, for the next one, we're gonna do the exact same thing. I mean, it's really the exact same thing, just different numbers and different variables. Well, f is equal to x and y plus 2, where x is this, that's x, and y, this is y, so it becomes 1 minus cosine t plus 2, right? And then we want to know what dr is. Well, dr is the derivative of this thing and this thing with respect to t. That would be 1 minus cosine t, and this will be minus, no, not minus, it will be just sine t, right? The derivative of negative cosine t is just sine t. And put your differential dt there. And let's take the dot product of those two vectors. So we go t minus sine t. 1 plus 2 is 3. It's 3 minus cosine t. Dotted with 1 minus cosine t sine t dt, which is going to be, well, t times this thing. So we'll do a little bit of filing. Okay, so it'll be t minus t cosine t minus sine t plus sine t cosine t. And this would be 3 sine t minus cosine t sine t. And remember, since this is a dot product, you can add all these. It's no longer vectors where these have to stay like that in their assorted row and column. It's a dot product, it's a scalar product. So you can literally just sum these things. And if you sum them, what do you see? Well, you see that we have a negative cosine here, and oh, look at that, that goes away. So I'm going to rewrite this all as t minus t cosine t 2 sine t dt. That's it. That's all it is. Look at that. And now we're just going to take the integral of that thing. And we do it from 2 pi to 0 because they tell us to do it from 2 pi to 0. So it's t minus t cosine t plus 2 sine t dt, which is equal to t squared over 2 minus t cosine t. I'll leave that like that, and then I'll solve for it in a second. Okay, I'm just going to leave it like that. And then we see that we got, what do we got here? Oh, we got 2 minus cosine t, because the antiderivative of 2 sine t is 2 cosine t. So let's just say we have part 1, which is equal to t squared over 2 minus 2 cosine t, 2 pi to 0. And then we have part, let's just answer this real quick. That will be 2 pi squared is 4 pi squared. 4 divided by 2 is 2, to be 2 pi squared. Cosine of 2 pi, cosine of 2 pi is 1, so minus 2. Then we got minus, it would be minus 0, and then it would be minus, minus, which would be plus 2, which is equal to 2 pi squared. So what I did right there is I evaluated for 2 pi first, which is 2 pi squared minus 2. And then in my head, I evaluated for 0, and 0 squared is 0, and 0 into this function right here is just 2. But remember, when you integrate, it's f of b minus f of a. So there's a negative in there. So it turns into that negative 2 here, which would be turn into a positive 2. So 2's go away. We just get 2 pi over squared. Yeah, unfortunately, we still need to do part 2, which is equal to 2 pi. Now remember, it's negative part 2, because it is. Now, if you don't know this trick, it's my trick. It's not my trick, actually. I learned it from someone else. T10, cosine t, sine t, negative cosine t. I'm going to explain this in a second once I set it up. So this is integration by parts, but written as a table. So what you do is you take the derivative of one of the functions. You usually pick the one that can, you always pick the one that can go to 0. And then you take the antiderivative of the other side, right? So it's integration by parts, but you just write it as a table. It's a lot faster. So you'd see that this turns into, like, you literally just go derivative of t, derivative of 1 to 0, and then you go antiderivative of cosine, which is sine, antiderivative of sine, which is negative cosine t. And then you always go plus, minus, plus, and you do the arrow of t times sine t, and you do the arrow of -1 times negative cosine t. The arrows always go in this order. You skip the first one on the right-hand side. This all is equal to t sine t plus, there's a negative here and there's a negative here, to pi to 0. If you put in 2 pi here, you get, well, for the first one, sine of 2 pi is 0. So if you have 2 pi times 0 plus cosine 2 pi, which is just 1, minus sine of 0 is just 0, cosine of 0 is just 1. Okay, I mean, look at that, that's 0. Your answer is the sum of both parts, which is part 1 minus part 2, which is equal to 2 pi squared. That's your answer. Okay, similar scenario for this problem again. Let's see. Well, looks like we only got one path. I mean, one C. Why do I always turn red? C is equal to RO plus, not C. R is equal to RO. Oh my god. V, which is 0, 0, 1 plus T, and we find V by, it's the change in position from 0, 0, 1 to 2, 1, 0. Okay, so when we're talking about X, the change in X is 2. What's the change in Y? It goes from 0 to 1, so it's 1. And then this goes from 1 to 0, so it's -1. So, okay, I gotta move my face down here. So the sum, adding those two vectors, the vector addition would be 2t plus t, and it's 1 minus t. Right, there we go. So see, 2t plus 0, t times 0, I mean t plus 0 is t, and then 1 plus -t. There we go. And that's equal to x, y, and z. So let's rewrite f. F was originally x minus y squared, y minus z squared, z minus x squared, and that is the same thing if you write it as a function of t. So if you substitute x in for t, you get 2t. If you substitute this into here, you get t squared. Okay, now y, substitute y in here. Well, I mean, substitute t for y, get t. Substitute 1 minus t into this, minus 1 minus t squared. Yes, we'll follow that out later. Z is this thing. And 1 minus x squared is, we'll FOIL, nope. It's, and now let's FOIL things out. You get 2t minus t squared. You get t minus t squared minus plus 2t. See, this would be this whole thing right here, 1 minus t squared. That is going to become t squared minus 2t plus 1. And if you times that all that by a negative, you'll get negative t squared plus 2t minus 1. Okay, so next one. I gotta make that t look a little bit more like a t. There you go. And then this will be 1 minus t minus 4t squared. That's f of t. Now you want dr Well, dr is equal to the derivative of this thing. 2, 1, minus 1. T. So then f dot dr. What is f dot dr? So it's 2t minus t squared. And this is t, which is 3t minus t squared minus 1. And this is negative 4 squared minus t plus 1, dotted with 2, 1, negative 1 dt. And then let's write the answer here. Let me indicate that that's the answer. So we would get 4t minus 2t squared, get 3t squared. Yeah, actually not 3t squared, it's 3t. Right, it's just 3t. And then this is just minus t squared. So it's basically just the same thing again, minus 1. Now this one we're going to times everything by negative 1. So we get 4t squared plus t minus 1. Okay. And let's write that as a complete scalar in one line. But before we do that, let's see if we can cancel anything. 4t, 3t, t. Look at that, all the t's add up. Like all the single t's. Now let's see if all the t squareds add up. Okay, no. So 2t squared minus t squared plus 4t squared, that's just t squared. And then we get minus 2. And of course, this is all differential dt. Okay, and now we just need to integrate all of that on what bound. So remember when I said, what's the value right here? Well, the value is 1. And remember, if you use this vector equation, your bound will always be 0t1. Thus, your integral will always be, not your integral will always be. Your integral would be bounded from 1 to 0 if you use this. Since we're using it, it is. Okay. 8t is t squared minus 2 dt. And that is, what, 4t squared, right? Yep. Plus t cubed over 3 minus 2t, 1 to 0. And we don't need to worry about the 0 bound because everything is times t. So, like I said, we just don't need to worry about it. Now, remember when we evaluate this, we're telling you that this is the work done. F dot dr is the work. Okay, so we get 4 plus 1/3 minus 2, which is equal to 2 plus 1/3, which is equal to 6 minus 1 over 3. Oh, not 6 minus 6 plus 1, which is 7/3. That's the work done. Okay. Let's do number 2 now. Okay, this next problem, it's a ds integral. So remember I said you have a ds integral? Earlier I said we'll kind of see something like this. ds is equal to dx dt squared plus dy dt squared, all square rooted and times dt. And I said that's kind of like the Pythagorean theorem for differentials in this case, which it's true, right? We'll see it here. But first, let's maybe draw a picture. The right half only, okay? This is a circle with radius 4. And we're only doing the right half. So we asked this question, what is this point? And by the way, I know that it's centered at 0 because it's not shifted. You can see it's not shifted. The equation does not show it's shifted. So this is 0, 4 to not 4, 0, 0, negative 4. Okay. Yeah, minor mistake real quick. Let's not say 2. It's actually 0, negative 4 to 0, 4. And that's if we're assuming counterclockwise is positive direction, which is usually what we always do for problems, right? we were counterclockwise. Okay, now, are we going to use this equation like we have been? I say no. You know why we're not going to use it? It's a line. It's a line, right? I mean, it's not a line. It's a circle. And lines don't describe circles very nicely, right? What we could use is we could actually use our polar coordinates. And you know them as functions of r and sine theta. Now, what you could just say is, theta and t, they're both variables. So you could either write this as ds, dx d theta, and d theta over here, and theta over here. Or you could just write these as t's, and write them as r cosine t, and r sine t. And in our case, these are both going to equal to what? We know our radius is 4, so it's 4 cosine t, 4 sine t. And then we could say that we know that dx is negative 4 sine t dt. And we know that dy is equal to 4 cosine t dt. So we found our differentials. We found our derivatives, actually, right? So if we're to put these dx, if we divide this dt and put it on the other side, same thing as this one, we would put it into this stuff. It's going to become, and if you square everything, you get 4 squared sine squared t plus cosine squared t. You get that, and then you know that this will just equal to 1, right? And then 1 times 4 squared is 16. 16 square root is 4. Okay. So ds is equal to 4 dt. There we go. So now let's rewrite our integral. And right, earlier we said that if we use this equation, our bounds will always be from 0 to 1. Did we use that equation? We did not. We used something like a polar equations to describe it. So maybe we should try to think about if this was polar, how would we describe this using polar? This would be from 0. This would be from negative pi over 2 to pi over 2, right? That would be the answer. Or you could write it as 3 pi over 2 to pi over 2, but just write it as pi over 2 or negative pi over 2. Make your life easier by doing that. And x turns into what? X turns into this y, oh my god, y to the power 4. So we gotta do this thing times 4, not times 4, to the power 4. And this is ds, 4. And as you can see, oh my god, it's gonna get huge real quick. 4 times 4 times 4 to the power 4. How many? That's 4 squared. This will become 4 to the power 4, so it'll become 4, 6. 4 to the power 6. I'm not even going to try to do that. From pi over 2 to negative pi over 2. Cosine t sine squared. Nope, not sine squared. Sine to the power 4t dt. Okay. So we have a cosine odd power. We have a sine even power. So if we did a substitution, in theory, right, should get rid of that cosine. Now let's think about what we can sub. If we let, I'm going to pick a fun variable. If we let fancy L, or other known as Laplace operator, if we let that equal to sine t, then d cos is equal to cosine t dt. And then if we made a table to transform, and we go from t to Laplace, I'm going to stop saying Laplace, even though, like, that's the math symbol for Laplace, but for us it's just a variable. I'm just going to say L. So then that would be from pi over 2, negative pi over 2. And if we put that into this, and put this into that, it'd be 1 and negative 1. Okay, so let's write our integral here now. We have 1 to negative 1, 4 to the power 6, in front of that all, cosine t. Erase it real quick. Plus, stop saying that. 4 L to the power 4, and then, like I said, okay, see that's a cosine dt, which is cosine dt, so it's just that, which is equal to 4 to the power 6, and that to the power 5, divided by 5, from 1 to negative 1. And as we can see, it's an odd powered function, so when we actually do plug in these bounds, it's as if it does make a difference, right? So we'd have 1/5 minus 1/5. And by the way, you could always do this, like if you recognize this, the power of the function, you could have wrote it as wait 1 second. You could put the 2, you could say times 2. So if you, like, cause like it's gonna, like I said, since it's odd power, it's gonna be 1/5 minus 1/5, right? 1/5 minus 1/5, which is 2/5. So if you want, you could just evaluate from 1 to 0 and times everything by 2. That's only useful really if you're not dealing with ones. We could have done it the same way and it'd still take the same amount of time. This is a trick for later. So it's 2, 4, 6 divided by 5. Yeah, this is just the answer. So it's 2/5. Okay, and it's 4 cubed squared. I know what 4 cubed is. 4 cubed is 64. So we have 64 squared over 5 times 2. Yeah, and we're just going to leave it at this. I tried to do this, and I mean, if you got a calculator, just go do this. But just leave it like that. It's fine. That's your answer. Okay, so let's do the next section. Oh, blank page. I'll delete that blank page later. Okay, so now we need to figure out if a vector field is conservative. Now, we do know a vector field is conservative if, let's go to our notes real quick. Should be on page 2. So so we know a field is conservative if del f is equal to f, del f of little f is equal to big F, and if the partial of y is equal to the partial of q with respect to x. If those are equal, that's the field's conservative then. So we know that's true if those conditions are met. So let's go back to our thing here, and let's see if we can get this to happen. Okay, so we have a function of f. We have a vector f, and it's a function of x and y. Now we need to find a little function, little f, and see if its derivatives is equal to f. Well, I like to start off by naming the stuff. We could call that, I don't know, I've been calling it P and Q. You can call it whatever you want. You can call it P, Q. Move my face down here. And then, like up here, it says that we need this to equal to del f. And if it's equal to del f, then that's equal, and del f is equal to df dx, which is equal to df dy. So we have our facts established, and we know what to do with this. Let's just take the things that are equal to each other. So p is equal to df dx, and q is equal to df dy, just to underline them. I don't want to underline two things. So if we say p is equal to df dx, and by the way, this is how I remember it every single time without needing to look up what to do, the steps here. Well, if you put dx on the other side, then you have df is equal to p dx. And then, yeah, if you integrate both sides, then you see that you get f is equal to p dx. And what is p? Well, p is equal to y(ex) plus sine y. So now we got to integrate this all with respect to x. That's just going to be y(e) to the x plus x sine y plus. Okay, now if we integrated with respect to x and we have a function of x and y, then we must have a constant that is a function of y. I'm going to call it g of y, and that's what we usually do. So I just like to think in opposites here, right? P df dx. Like, so we go p dx, and then later on we'll have gy. If that doesn't make sense, you need to find some other way for yourself to kind of remember how this process goes. For me, it helps me to think in opposites. Okay. And by the way, I skipped a step, which would have been important to do, but first we need to find if if dp dy, not dp dy is equal to dq dx. Let's check this. This is like the most important step to do first, or else this stuff doesn't even matter. So I should have done that first. Okay. dp dy is, so we take this thing with respect to y, which is e to the x plus cosine y. And then we take this thing with respect to x, which is e to the x plus cosine y. And then they're equal. Okay, so that's true. So it is conservative. That's important to know. I kind of could tell that they were conservative, so I didn't do it. How is because you could usually see that if there's an e to the x here, and there's an e to x here, and if there's a sine and there's a cosine. So if there's opposites, and then if you take their opposite derivatives, they're usually going to be equal to each other, because opposite, opposite, opposite. Like I said, these types of things I like to think in opposites. If that doesn't work for you, you need to find some sort of way. Okay. So I'm going to put this little fact all the way over here. I'm going to put it at the top right here, because we don't really need it anymore. So this is what f is equal to. Y e to x plus x sine y plus g of y. I need to work on my y's here. They look like these. Okay, so if we found f, but we don't know what g of y is, maybe if we differentiate this little f with respect to y, why would we differentiate with respect to y? Because we want to find g of y, and I'll see why in a second. So if we differentiate this whole thing with respect to y, e to the x plus x cosine y plus g prime of y. And then now you think, okay, wait, so what did we do? We found df dy. Didn't you say that df dy is equal to q? Yeah, I did. And that's true. They are congruent. The symbol means congruent. So then you could write it as q. Q is equal to df dy. And q is equal to this right here, which is equal to EX plus cosine Y. And okay, so we have this thing on this side, this thing on that side, this thing on this side, this thing on that side. It tells me that G of Y, the only function of G of Y that it could possibly be is 0. Okay. And if G prime of Y is 0, then if you integrate G prime of Y, if you integrate G prime of Y, it has to be some constant. And if we take the derivative of some constant, it's 0. So this should make sense here, right? There should be some logic here. Thus, we can say that f of x comma y is equal to y e to the x plus x sine y plus c. Now let's check. Well, what is del of f? Well, del of f is, if we take this with respect to x plus sine y. Did I mess something up? No, I did not. Y equals e to the x plus x sine y. And if we take this with respect to y, we get e to the x. 1 second, we get y e to the x plus sine y. Okay, and now we get e to the x. If we take this with respect to y, we get e to the x plus x cosine y. Is this the same thing? Is that? Okay, that's that. That's that. That is that. And that is. Okay, yeah. Yep, it's exactly the same thing. So our conclusion is true, right? It is. We found a function. Why is my pen not working? That satisfies this. And that's our answer. The field is conservative. I'm not going to rewrite again. The field is conservative. And dp dy is equal to dq dx. We showed that up here. I'm going to make that bigger because we actually do have space for it. Okay, so now we're starting to get into the true essence of the fundamental theorem of line integrals. So we need to find a function, kind of like this one, that satisfies this condition, which means that the vector field is conservative. And if the vector field is conservative, then we can use the fundamental theorem of calculus to evaluate a line integral. Instead of using f dot dr, we could use integral sine del f dot dr, which is easier. Okay. So yeah, we need to find a function here. Let's write it f is equal to pq, which is equal to del f, which is equal to f(x), f(y). That means partial of x with partial y. I believe that's called Newton's notation. Okay, so there's another method we can use to find these functions. So we could let f be like this. Then you go p dx q dy, kind of like what we did earlier, except you just know the method now, so we're doing a little shortcut here. But instead of doing this is actually called exact differential equations, like this part right here. But instead of doing that differential equation method, you can just integrate here and then try to group the like terms. Not group, identify the like terms and identify the non-like terms here. And I'll show you what that means in a second. Integrating p, and p is 3 plus 2xy squared. Not 2, it's 3. Xy squared dx. And integrating 2x squared y dy. If we take this integral, what are we going to get? We're going to get 3x plus, this will become x squared, y squared. This will become, if we take this with respect to y, it will become x squared, y squared. What do we have in common? We have, you just write what's in common and what's not in common, but you don't overlap. You don't do duplicates. 3x squared plus x squared, y squared plus c. That is your function of f. And let's test that theory. So if f of x comma y is equal to 3x plus x squared, y squared plus c, then del f would equal to what? Let's see. It should equal to 3 plus 2xy squared. And then let's take it with respect to y. Comes 2x squared y. And is this the same thing as we were given earlier? Oh, look at that. It's exactly the same thing. Right? All of this is equal to all of that. So our field is conservative. Thus, it would make sense to do this. If f is the same thing as del of f, then let's use del of f. Now, you may be like, oh my god, that's the same integral. And you're like, yeah, it is the same integral. But if you have this, and they equal each other, you could use the fundamental theorem of line integrals, which is f of b minus, not big of f, not big F, little f, f of b minus f of a. Okay. But we need to find what b and a is, right? We kind of don't know what it is yet. I need to drink some water. Okay, I'm back. I needed that water really bad. f of b minus f of a. Fundamental theorem of line integrals. Now you're like, what is f of b? I would say maybe that's point B, and I would say maybe that's point A. Huh? Let's see, right? Well, not let's see. Let's call it A, B, right? Now let's explicitly find what f of b is first. Now, f of b would be then f of 4, comma 1/4. And then let's plug this into that. Into this right here. Well, you'd get 3 times 4. Oh. You get 3 times 4 plus 4 squared plus, oh, not 1/2, it's 1/4 squared, which is 12 plus 16 plus 1/16. Oh my god, look at that, that's so nice. Which is just 13. F of A, if that's A, then this would be f of 1, comma 1. And this is f right here. So then if this is f, right? And if we plug in these points into this, we get 3 plus 1 squared plus times 1 squared, which is 1, which is equal to 4. And yeah, okay, look, there's a plus c here. I added the plus c at the end over here, and I'll add a plus c at the end over here too. Okay, so all of this work for just, like, look at this. This is calculus by subtraction. 13 plus c. Minus all of this. So minus 4 minus c. C's go away. And 13 minus 4. Oh, that's 9. Right? There we go. That is our final answer. All of that just for this. Okay. What does the question say? It says that show that the line integral is independent of the path, and then evaluate that integral. It looks like we're going to use the fundamental theorem of line integrals here. But you're like, what is f? What is r? What is del of f? And what's the path? Well, we can use any path. So let's just first find a path. Not in red, but in black. So we can use r is equal to ro plus tv. Right? Then we see that ro is 1 to 0, 1 comma 0. And then what's v? Okay, so we go from 1 to 2, it's an increase in 1, and we go from 0 to 1, which is a decrease of 1. What does this mean? Well, this would be t plus 1, and then this would be 0 minus t, or let's call it minus t. This is r. Okay. But we don't really know what f is yet. Well, we know f is equal to pq. Okay, I'm gonna go out on a limb here, and 2x e to the negative y, I would usually write it as p dx plus q dy. If we're writing the general form of a line integral, we could write it like f dot dr, which is the same thing as p dx plus q dy. I mean, we've seen this like form in like other problems. Let's go back. Step. Wait, where is it? Right here, right? This would be like p, q, and r, right? Or a, b, and c, whatever you want to call it. And I'll show you, it'll make more sense once I do it. So as we see, we could just call this thing P, and we could just call that Q, and we'll do it. Okay. So I was just showing you guys the form. Sometimes they actually like give you a lot of information here. They just want you to see the information, or maybe try a little bit harder to realize what they're giving you. That's P. What's Q? Well, Q is 2y minus x squared e to the negative y. And the fundamental theorem of line integrals, not the fundamental theorem of line integrals, but a conservative vector field where dp dy is equal to dp dx. And if that's true, then we can go and use f dot dr is equal to del f dot dr, hence del f is equal to f. Looks like we need to find a function f, but before we do that, let's just make sure that we actually have a conservative vector field. So I'll write dp, not dpto, it's dp dy. What is this with respect to y? It's 2x e to the negative y divided by negative 1, so it's just negative 2x e to the negative y. What is this with respect to x? Well, that is dq. Why am I writing dq do? dq dx. And if we differentiate this with respect to x, we get negative 2x e to the negative y. Oh, look at that, the exact same thing. Okay, so the field is conservative. Luckily, now we can try to find our function f, right? Okay, so f is equal to p dx q dy. Remember, if this is equal to f, right, then you could put the differential on the other side. My bad. I'm totally missing it. I'm like been going at this straight for like a super long time. It's definitely not p here. It's q. I'm sorry about that mistake. All right, if this, we can put the differential on the other side and then find and solve for f. That's what I meant to say. So p, what is p? Oh, p is this, 2x e to negative y dx. What is q? Q is this, 2y minus x squared e to the negative y dy. Well, this turns into x squared e to the negative y plus c. And what does this turn into? This turns into y squared minus, right? X squared. If we integrate with respect to y, this part e to the negative y, that becomes a negative 1 under here. The negative 1 times negative, that's what we get. And then you see that we have two common terms, and we have the same constant, we have y squared. So f of x is equal to y, f of x comma y is equal to x squared e to the negative y plus y squared plus c. And let's check if we take del of that. If we take its derivatives, if we take f and its derivatives with respect to x over here and with respect to y over here, we should get the same thing. So the derivative of this with respect to x is 2x e to the negative y. This with respect to y, well, I need more space before I even do that. It is negative x squared e to the negative y plus 2y. And that's the same thing as this. It's just reversed order. So, yes. That's good. Good. We're almost done already. Look at that. So, we want to evaluate now. By the way, we did not need this step. I don't know why I did that. It's my bad. It's not bad to do this, but it didn't really help that much because we're using the fundamental theorem of line integrals and we're not just doing a straight up line integral like we usually do. But it's fine to do this step. It just didn't give any progress. That's what happens when you do math for a super long time. You keep going straight and without taking breaks. You do things that you don't need to do. Okay, so this is del f. Now we can write our integral. And it's from any closed path. So this turns into del f. Not any closed path, it's independent of the path. So we can use this thing, which indicates f of b minus, this is f, little f. So what is f of b? What is f of a? Well, let's call this b, let's call this a, and I'll label it. I'll go up to the top. A, b. So let's find f of b first. Well, f of b is the same thing as f of 2 comma 1. And f of 2 comma 1, if we put 2 comma 1 into this thing right here, what do we get? We get 4e to negative 1 plus 1 plus c. Well, that's what we get. And if we get f of a, what do we get here? We get f1 comma 0, right? F comma 1 0, and we plug it into this. Okay, so if x is 1, this would be 1 e to the 0, which is 1, plus 0 squared, which is 0 plus c. Okay. So then now we subtract those two things. And we'll write it like this. Let's just be fancy. Did not meant to erase everything? No. Subtract. Yeah, come on, let's not forget we can work vertical. We get 4e to the negative 1 plus 1 minus 1 minus c plus c. Yeah. The c's cancel, okay? I just wrote the order a little weird here. The 1's go away, the c's go away. That's our answer. 4 over e. There we go. That's our final. Okay, second question. Now, give you a little bit less information. They don't give you integral anymore. They give you 2 points. And they give you a vector function. I mean, just a vector, right? Now, let's use this information. Well, maybe what we should do is find the position vector that describes this change. Why do I keep writing red? R RO plus TV. Now, we're actually going to use this here. Well, this is 1, 0 to 2, 2, and if the work... Okay, let's just check if this is a conservative field first. Is D... Okay, I'm going to call this A and B because they took the letters P and Q, so I can't use P and Q anymore. It's dA dy equal to dB dx. Well, let's see. Do not want to move everything. Just move something. Oh my god, I'm gonna freak out if this thing moves everything. Okay, what's dA with respect to y? 0. What's this with respect to x? 0. Okay, so it's a conservative vector field. That's all we needed to know. Therefore, any path can work here. So let P be our starting point and Q be our ending point. Okay, what's the change? It goes from 1 to 2, that's 1. And it goes from 0 to 2, that's 2. Okay, then we could write this vector as T plus 1, T plus 1, and 2T. Okay, that's our vector function. That's what we need. And maybe we should rewrite f as a function of t. Well, f was originally x cubed, y cubed. Well, if x is t plus 1, then this turns into t plus 1 cubed. And if y is 2t, this turns into 2t cubed. Okay, and then this would be, oh my god, this is going to expand terribly. T squared plus 2t plus 1, t plus 1. And this would be 8t cubed. Okay, and then we gotta do this. Oh my god, I really hate foiling. It's like the one thing in math I really don't like. I always mess up on it. T cubed plus 2t squared plus t. Then we get plus t squared plus 2t plus 1. Thank god it wasn't that bad though. I'm going to rewrite this thing, just kind of write it nicer. Okay, well, it'll just be t cubed plus 3t squared plus 3t plus 1. Yeah. Yep, that is it. Now we got t cubed down here. Okay, so that's f, and we want dr. Well, dr is 1 and 2 t. Remember, we differentiate this with respect to t. So then f dot dr. Oh no, I need more space. Just t cubed plus 3t squared plus 3t plus 1, 8t cubed dotted with 1. Not 1/2, it's 1, 2. T. What does this turn into? Well, this thing stays the same because just times 1. This thing just turns to 16t cubed. So 16t cubed plus all of this, that is 17t cubed plus 3t squared plus 3t. It's 3t plus 1 dt. And let's integrate that now. It goes from 0 to 1, right? Because remember, we always use this. If we use the vector function, then we will always be from 1 to 0. 17t cubed plus 3t squared plus 3t plus 1 dt, which is equal to 17t to the power 4 over 4 plus 6t to the power 3 plus 3t squared over 2. And my brain's going out the window right now. T squared, 3 over 2, t from 1 to 0. Okay, and everything is times t, so we can forget about our 0 bound and just think about this fully as 1. And if we just put 1 into everything, it turns into 17 over 4 plus 1 plus 3 over 2 plus 1, which is equal to 17 over 4 plus 6 over 4 plus, that's 2. 2 turns into 8 over 4. And that turns into 17 plus 14 over 4, right? Yeah, that is. And then this turns into 31 over 4. There we go. That is our final answer. Okay, last problem of the video. I mean, this has been going on for way too long, but I mean, we'll definitely be prepared after this. Okay, well, what does the question want us to see? Well, why is f dot dr for any of these curves, 1, 2, or 3, all going to have the same value for their integral? And then we want to find that value. Well, we know that will be true if the vector field is conservative. Well, let's prove that the vector field is conservative. I will say that this is P, and that this is Q, and dP, dy is what? Okay, so if we if we differentiate P with respect to y, 2x, and this should be equal to dq dx. Now let's check that. If we take dq dx, oh, and it is 2x. Okay, so I don't even need to write it again. Boom. Okay, well, for a, we could say f is a, it's not a, grammar class here, conservative field. That's all we need to say. Okay. Oh, if it's a conservative field, thus the path is independent. Maybe we should say that too. Thus, f dot dr is independent of the path. God, writing's looking ugly. Of the path. Oh no. It's not how long I've been doing math. Path CI. So any path. Great, you guys can't even see what I was writing. Any path C. That's what CI said. Any path C. So F is a conservative field, thus f dot dr is independent of the path CI. So if you guys see, there's path 1, there's path 2, there's path 3. Okay, now let's actually integrate here. explain, wait, yeah, we actually need to integrate this. Okay, so f dot dr, since our field is conservative, we could do this. And if we do that, then we can do f of b minus f of a. Stop writing capital F. It's not capital F. It's lowercase f. Well, what does that mean? It just means we need to find f. We need to find a function f that satisfies this. So I'm just going to jump to the shortcut because you have seen it so many times. P dx, right? Q. I wrote P dq, man. Like, I'm fried right now. P dx. This is Q dy. My God, toasted. P dx. That's P. 2xy dx. This is equal to x squared y plus some constant c. This is x squared dy, which is x squared y plus some constant c. Okay, then you can see from the fact that these are the exact same thing, thus fx comma y is equal to x squared times y plus c. And if we were to take del f, that would equal to x. I mean, if we were to take del f, I'm going to stop talking and do it. So with respect to x, differentiating f with respect to x is 2xy. Differentiating with respect to y is x squared. And as you can see, that is exactly what we got up here. So again, checks off. That's all we want to know. Okay. Well, we now need to find what f of b is. F of b is f of 3 comma 2. So if we put that in, okay, well, 3 squared times 2, that's 9. 9 times 2 is 18. 18 plus c. F of a is equal to f comma 1 comma 2. Okay, so it'll be 1 squared times 2, which is equal to 2 plus c. And then if we minus these guys, let me not write the negative there, let me write the negative here. If we minus them, we see that we get 16. Just 16. 16 is equal to the work. And that would be the work for any and all paths, like I said, as long as they all start at the same point and end at the same point. And why? It's because they're conservative, because our field is conservative, and f dot dr is independent of the path ci. Okay, so found this video useful. Share, like, comment, subscribe, just fucking leave anything so I can make some money off this shit. Thank you.